Okay, give me just a second to get things set
Sure.
up. Okay. Mm, this format was a bit challenging, but I think I did okay with it.
Okay, great. And Annalee's mentor is Amita Agrawal in computer science.
Yes.
Okay, we will try hard to stay on time as much as we can.
Okay.
We have 5 minutes for the presentations, 2 minutes for questions. Anybody is welcome to ask questions at the end of each presentation.
And then the moment I hit play, it's just gonna start. So, okay,
Go ahead.
let's start with two scenarios. First, imagine you have a question and a list of choices, and you want the generated answer to be the correct one. How would you go about that? Next, imagine you have English and Spanish phrases that you want to combine in an automated fashion. How would you go about that? This was the basis of my research project. To fulfill these scenarios, we must discuss the key ingredients, MMLU tasks and machine translation, as well as their role in MLLMs. MLU tasks provide insight into how language models understand language, and machine translation reveals how these models approach language generation. So let's define what an MLLM is. A multilingual large language model is a type of AI model that has been trained on multiple languages rather than a single one. Some MLMs you may be familiar with include, but are not limited to, ChatGPT, Google's Gemini, Meta's Llama, and Mistral Nemo. Some MLMs are capable of performing cross-lingual understanding, which involves understanding multilingual queries in text, even if the training set and test set are in two completely different languages. However, what happens when we try to introduce hybrid languages into our models? This is where we introduce a linguistic principle known as code switching. Code switching is when a speaker alternates between two or more languages or language varieties within a conversation. For this project, I decided to focus on Spanglish, which is a hybridization of English and Spanish. Code switching shows itself to be a bit of a tricky challenge when it comes to studying and modeling how it works in MLMs. For starters, there is a lack of human-reviewed code switch datasets, leading to quality and availability issues for research in this field. Even though large proprietary models like ChatGPT can provide high-quality machine-translated data, it serves as a workaround and not a permanent solution. The next issue concerns the model's inability to comprehend the context and semantics of the languages in play. Here you can see that code switching can be used for emphasis purposes, which is an element that models may not always understand. Regardless, let's call back to the beginning. My objective with this project was to explore multilingual understanding with English, Spanish, and Spanglish by testing question answering and code switching tasks on the model of my choice, question answering being an MLU task and code switching a machine translation task. The model I ultimately selected to run my experiments on was Pangaea 7b, a fully open source, multilingual, multicultural, and multimodal LLM. At least that's what it advertises itself as. Spanning 39 languages, the model is reportedly able to execute MLU tasks with significantly higher proficiency than some of its competitors. I picked this model for two main reasons. I wanted to mimic some of the paper's results to familiarize myself with running models and datasets, and I wanted to see if the model was capable of understanding and generating Spanglish text. I began by selecting two main datasets, each supporting one of the downstream tasks I was testing. For the question answering task, I used Cohere Labs' global MLU dataset from the Hugging Face portal. I thought using this dataset would be interesting because it's not part of the instruction set used to train the Pangaea model. So after importing the model and dataset, it was essential to craft an explicit evaluation prompt for the model to follow. Previous experiments with Pangaea have shown that the model performs better when the given instructions are more detailed. I later learned that this was because Pangaea is a pattern-based model, not an instruction-based one like ChatGPT. These differences led to the use of Mistral Nemo to determine whether the issue was a coding error or a model error at times. After fixing some of the bugs in the code with the help of ChatGPT, I was able to average 40 to 50% accuracy for both Spanish and English in a sample test set of 10. In future instances, I measured the accuracy using a test set of 100 and achieved approximately 50 to 60% accuracy for both English and Spanish. Considering these results were similar to the accuracy reports for multi-subject reasoning in Pangaea's paper, it was confirmation that the model was capable of performing MLU tasks. However, I decided to examine its chain of thought prompting to see if it would improve accuracy scores for the QA task in the model. But it actually lowered the average accuracy scores of the model, ranging from 44% to 54% between English and Spanish. It began to generate labels that were not A, B, C, or D, which affected the overall accuracy, pointing towards an error in how the prompt was designed rather than a fault in the concept itself. For the code switching task, I decided to use Drew Curran's Spanglish dataset to test whether or not Pangaea was capable of handling and understanding code switch text. However, before we proceed any further, I must introduce what matrix and embedded languages are and their correlation to this dataset. To make a long story short, the matrix language is the primary language we'll be using for its sentence structure, which would be English in our dataset's case. The embedded language is the other language from which we'll be taking elements from to insert into the primary language's sentence structure. In our dataset's case, the embedded language is Spanglish. Now that we know the basic linguistic principles the dataset is modeled after, we can begin setting up the references to our hypothesis. Shown here is what we consider to be our reference, as the Spanglish side is what we aim to have the model output when we ask it to translate English sentences into Spanglish. Unfortunately, since this is a current work in progress to be finalized for the research paper, there is not much I can say other than the next steps would be to determine if the output issue lies within the code, the evaluation prompt, or both. However, we can see from this table how we can easily compare our hypothesis to our references to evaluate our model's performance. Overall, there is a lot of room for improvement in this project. From fine-tuning the prompts to fixing the bugs in the code, many steps can be taken to assist Pangaea in addressing its shortcomings in comprehending code switch text. If I had more time, I'd test other models with more datasets and expand the overall scope of this project. Thank you. And then these are my references. And any questions?
Thank you. Any questions for Anneli? How does it compare to like just a regular ChatGPT or any other LLM performance? Because you can also translate there, right?
Yeah, so I mentioned it like the pattern-based versus the instruction-based. Like
Right.
with ChatGPT, you can just like tell it to do something. With Pangaea, you have to be like more specific because it's literally like copying patterns. So when I like initially started like running tests to like see how it would do with Spanglish, I was confused why it would like start generating just English sentences after a bit or just Spanish sentences after a bit.
Okay.
And after like looking into it, it was because it was like going after like the ratio of like English to Spanish and then going off of that.
I see. Wayne has a question. Wayne.
That relates directly to my thought. How do you know which part of it should be English and which part of it should be Spanish? Is it the nouns or the verbs, or did you give it some guidance, or did it just try to pick some random sample to put in each language?
So with the chain of prompt, like the chain of thought prompting that I was like exploring, we did include like a rule set and we were developing a rule set. Because there's like obviously like aspects where it's like, like the nouns and then the verbs, and everything like that. But sometimes it like doesn't adhere to that and then it just sounds like really unnatural, which was like another issue because I was like, well, this doesn't sound right. But yeah.
Awesome. Thank you. Good. All right. In the interest of time, we'll move on to Kieran. Thank you, Anneli. Kieran, you should be able to share your screen. All right.
You don't appear to have a microphone set up. It's not showing the microphone symbol.
Kieran, yeah, we can't hear you if you're saying something.
Yeah, if you unmute, you should be good. The mic is there. You're just muted.
Can't hear you. No.
Drat.
Edwin, can you go?
Yeah, I'm ready.
All right. Then Kieran can try to fix his microphone.
Wait, hold on. I'm trying to turn on my video, but my computer's kind of zoom. Oh, there we go.
We can see. Yeah.
So
Okay.
my camera's a little bit weird here. The lighting's kind of bad, but I'm
That's
gonna
okay.
share my screen.
Yeah. Sounds great.
Uh,
Okay.
how do I can't get rid of my taskbar down below. I can't access stuff.
We can see the slide.
Well, I can't. Oh, here we go. So I'm Edwin, and today I'll be presenting my paper titled Breaking the Heuristic Barrier for Subset Sum, a fast and scalable algorithm with inverse linear area decay. So, hope you enjoy it. So what is subset sum? So imagine you have a customer paying $10 for a $9.75 cupcake. That means you need to give 25 cents of change. So that means you have to choose a subset of the coins you have in order to add up to 25 cents so you don't underpay or overpay. So an algorithm that you might think of for this is to always choose the biggest coin that you can. For example, in this case, you pick 22, you have 3 cents left. Then you pick 2, then you have 1 cent left, and you can't pick anymore. So it's suboptimal. So the failure reason in this case is that the greedy algorithm really only gets one chance. So because it chose 22 at the start, it's permanently screwed over. So you need to give it more chances or else it won't be able to recover. So in this case, you should choose 15, 10, which adds up to 25. So if you give the greedy algorithm more chances, then it'll reduce the likelihood of some early mistakes, permanently crippling it, which means you'll never be able to get to the right answer. So you want to run kind of multiple greedies at once. But the problem is, in order to get a perfect solution, you would need 2 to the n greedies at once, which is way too much because 2 to the n grows very fast. Like when n is 20, it's already a million. So first, the shift proponent of beam search, shift of a of n k adds k to all the elements in the array. For example, shift of 1, 2, 7, 3, you get 4, 5, 10. There's also an expansion step. What it does is, given the current possible sums in the next element in the array, you return the new possible subset sums. So if you start with 1, 3, and x is 3, you get 1, 3, 4, 6. So this is beam search without trimming. You start with 0, which is the only possible subset sum at the start, and you repeatedly expand, increasing the size by 2 until you generate all 2 to the n possible subset sums. Then you return the best candidate. In this case, the time complexity is 2 to the n, and the space complexity is also 2 to the n, but it gets the exact solution. But it's still really expensive because, as we mentioned earlier, 2 to the n goes extremely fast. So the beam search takes a better approach, which is not keeping too many, only the best case so far. So usually it'll get good enough solutions, and the definition of good enough we'll be exploring more later. So in this case, we're going to add 2 more lines to this code. So you remove all the useless elements, which is everything above the target, because you're never going to get back down to the target, and you only keep the k closest elements to the target. So the time complexity is O of nk, and the space complexity is O of k, because the beam is the best sums array is of length k. But we're not too sure about the accuracy, so we're going to have to do a little bit of analysis on that. So in order to do the analysis, we're going to have to make the assumption that all the elements in the array are drawn from a uniform distribution from 1 to m, where m is a large constant. So the greedy algorithm is equivalent to the beam search with k equals 1, because beam search is a bunch of greedy algorithms, and the greedy algorithm is proven to have an O of m over n expected error. And intuitively, if you increase k, you'll get higher error. And in this case, if you increase k by 2 times, an error will halve, and you get inverse. So that means you get inverse linear error scaling. So this goes down extremely fast. So the heuristic barrier is that almost all the heuristics haven't been able to get past inverse linear error scaling, and the error decay is usually very unstable, which means they decay fast in the beginning, but then they flatten out. So, and the real world performance of beam search, on the other hand, is faster by orders of magnitude compared to other methods. It's very memory efficient, and it can go below 1e10% error in just a few seconds, regardless of n or even m. So in conclusion, beam search is a new practical baseline. It's simple yet effective, and it provides significant theoretical and practical progress.
Thank you, Edwin. Questions for Edwin?
How new is beam search? Is it a new discovery or has it been around a long time?
Oh, beam search is a common common method in natural language processing tasks, but it's never been applied in the field of theoretical computer science.
So the subset problem is, is applied everywhere in reality, like portfolio optimization and whatnot, right? Can you give us an example of a problem that you can solve with your approach that others could not solve because you're so much better with what you've been doing?
Well, there's this problem of song selection where you're trying to select some songs, and because you're, let's say, running a radio station and there's a break, you want to select some songs such that it adds up to the break time, but it doesn't go over,
Right.
it doesn't go too much under. And
Right.
my method manages to solve it in like mere like just instantly, while other methods take a pretty long time.
Okay. Okay, cool. That's a good example. Yeah. Great. Other questions for Edwin? Very cool. Thank you. Kieran, did you figure out your microphone?
Can you hear me now?
We can hear you. Great.
Great.
Okay.
Can you see that?
It's coming up. Yep.
Awesome. I will just start the autoplay.
Perfect.
A biological neuron receives signals, processes them, and decides whether to fire. We can achieve a simple computational model of this behavior with inputs, input weights, and an activation function. When the weighted inputs exceed a certain threshold, the neuron will fire. I don't know if it's autoplaying.
I think it's good.
Oh, I think you need to press play in
Okay.
order for it to start autoplaying. Yeah.
Oh,
yeah, just
okay.
hit play.
Sorry. I've not
You can just
done
advance
this.
manually. Right, play. Yeah.
Okay, I'll start over.
You can just
How can
advance
we?
manually. Yeah.
Okay, I'll just skip this one then.
Yeah.
Neural networks are made up of layers of artificial neurons. These networks can learn patterns and solve problems such as image recognition, text classification, or navigation. They learn by adjusting the weight of the connections between neurons throughout training using back propagation and gradient descent. Unlike typical artificial neurons, spiking neurons transmit information through spikes relative to time. This model is more biologically realistic and can do more with less. However, training spiking neural networks is difficult due to their non-differential spike-based activation functions. The Santa Fe trail problem is a classic benchmark in genetic programming. In order to solve a trail, the agent must eat all of the pieces of food on the trail within a certain number of steps. The only input the agent receives is whether or not the coordinates they are facing contain food. Historically, the most common way to solve trail problems has been with genetic algorithms, though a finite state machine that can complete the trail has been developed. Building on earlier methods, neural networks offer a promising alternative by learning to generalize trail following behavior through reinforcement learning. Reinforcement learning is a type of machine learning where an agent learns to make decisions based on rewards it receives for correct actions. Some reinforcement learning methods are more complex than others, leveraging penalties, reward shaping, and exploration bonuses. I built a custom environment for trail solving using the Gymnasium API. The observation space is a 1D array with a single value, whether or not the square ahead has food. The agent receives a +1 reward for each piece of food eaten, and the environment terminates when all food pieces are gone. The recurrent neural network I used had one input node for whether or not the square ahead had food, a long short-term memory hidden layer to process observations over time, and a fully connected output layer which returns the Q value for each possible action for each state being processed. For my spiking neural network design, the input and output layers were the same as the recurrent neural network, but the hidden layer was made up of recurrent, leaky, integrate, and fire neurons. Spiking neurons are more computationally intense to simulate, but they yield better results than the long short-term memory layer. While both neural networks were trained using deep Q learning, they must be trained in different ways. Spiking neural network training is spike event driven, while recurrent neural network training updates weights continuously at each time step. Spiking memory must also be encoded differently to recurrent memory. The agent was trained on a variety of trails of increasing difficulty. The difficulty of a trail was determined by whether it had gaps, turns, or turns with gaps. Larger gaps were considered more difficult. Trails with large gaps within turns were considered the most difficult. The trails I used to evaluate the agent were the Santa Fe Trail and the John Muir Trail, which is another classic benchmark for genetic programming. The agent was evaluated on these trails to assess if it had learned general trail solving skills. These results from early on in training show that the spiking neural network had a minor advantage over the current neural network, though later on in training, the performance gap between the two networks becomes much larger. On the evaluation trails, the spiking neural network performed better than the recurrent neural network. Though the recurrent neural network still had the capability to solve trails sometimes, the spiking neural network displayed that it had been able to learn general trail navigation strategies. Overall, the spiking neural network agent outperformed the recurrent neural network agent. Though the spiking neural network required more complex training than the recurrent neural network, on neuromorphic hardware, it may demonstrate a power consumption advantage. Though running on regular hardware, it does not. It takes longer to train, it takes longer to evaluate. Potential applications for this are edge computing, particularly relevant in automated navigation in an environment with sparse rewards, such as unpaved roads or a lack of signage. After the recurrent neural network, the next kind of neural network I tried was the convolutional neural network. However, this kind of neural network was not suitable for the environment that returns a single input. After the spiking neural network, I started the process of porting it to an FPGA. The FPGA I was using was a Nexus 4 DDR. In order to keep using the same environment, I had to write a wrapper for it in Verilog. I used UART to send and receive data from between the FPGA and the environment wrapper, which communicated with the Gymnasium environment and translated observations for the FPGA. I was not able to finish this part of the project. Potential next steps are finishing the FPGA implementation of the spiking neural network, or I could compare the networks I already have with a fractional order version of the spiking neural network, or I could work on a physical model like what was done in our lab for the carpool problem. I'd like to thank Dr. Tusher and everyone in the lab who helped out over the summer, as well as the Frank and Ken Summer Undergraduate Research Program for providing a stipend. It has been a great experience, and I've really enjoyed this opportunity this summer. Thank you.
Thank you, Kieran. Questions for Kieran?
Well, approximately how good is the spiking neural network? So can it solve the whole trail, or how far can it solve?
The spiking neural network is able to solve the whole trail, but it takes you have to train it for a very long time. You have to have a lot of good training trails, which I think made reinforcement learning maybe not the best like way to train for this, because I was trying to teach it general strategies instead of one specific task. But the spiking neural network did do a lot better than the recurrent neural network.
The spiking network wasn't recurrent though, or was
Or
it?
wait, no, it was recurrent. My bad.
It
I
was
meant
recurrent. Okay.
spiking recurrent neural network.
Okay. And your CNN that you tried, that was only feed forward?
Yes, and
Okay.
that just wasn't suitable for this application at all, because that's more for like image processing,
Right.
and I couldn't, because when it only accepts the input of like whether or not there's food in front of it, convolutional neural networks want like more of a 3D input, and I couldn't do that while still obeying the rules of the problem.
Right. Right. You need memory for that task, right? You need to know what happened in the past.
Mm-hmm.
Great. Okay. Other questions?
Upon solving, the Santa Fe trail, and could it solve other trails without further training?
It was able to, it was not able to solve the John Muir Trail, but it was able to get pretty close, which I think is promising for having generalized those like trail navigation skills. Though I don't think past, because the trails I was using were on a 32 by 32 grid. I don't know about performance past that kind of grid.
Okay.
Got it.
Cool. All right. Thank you again. Let's move on to
Thank you.
Richard, Yufei, and Lucy.
Yeah, sure, just give me a second to share my screen.
Oh, okay. Great. We can only see the top of your, okay,
see?
good, better.
Okay.
Yeah.
And try it.
All right.
Are you able to see the slides?
Yep.
Okay, cool. I will get started here. So hello everyone, this is Sifa and I have my teammates with me, which is Lucy and Richard. So throughout the REU project, we built a real-time mental wellness AI for lonely elders in China. You can think it as a conversation bot that's more sophisticated. And we came up with this idea because according to multiple statistical sources, the population aged 60 and older in China will reach approximately 30% in the year of 2035. And currently 26% of elders show symptoms of depression. Elderly mental health is being significantly overlooked. So our product tackles 3 major pain points. Loneliness, our AI-powered agent is always available whenever it's needed. And depression, we've integrated powerful detection systems and anti-depression mechanisms to help guide users toward positivity. Accessibility, we deliver AI-based emotional care that's extremely cost-effective and scalable to serve all seniors. Our system, I know it is very complicated, but it consists 4 main modules that work together. The first is text voice input handles user communications, and the emotion scoring module analysis and scores emotion states. Thirdly, strategy selector combines these emotion scores with conversation history to generate AI prompts and responses. Finally, long-term trend monitoring tracks users' emotional progress over time.
So I will introduce our input system. Our system accepts 3 input types. They are directly text entry and voice conversation via microphone, and upload the pre-record audio. And all input is intelligently pre-processed. The speech is converted to text via ASR, and input is segmented. Crucially, we normalize details and simplify the complex sentence to ensure a consistent understanding, make every interaction effortless, especially regards of technical literacy or speaking styles.
So as mentioned, we have 2 kinds of voice text channels. First is voice channel, and second is text channels. And to calculate text emotion scores, we use 3 channels. First is lexicon-based approach that extracts psychological features through lexicon matching. And second, an LM pathway that performs emotion inference using design prompts. Finally, because LM outputs can be unpredictable sometimes, we train a stacking ensemble model to provide more reliable emotion classification results. I'll elaborate a little bit more on the self-trained model. Our stacking ensemble combines 3 diverse space models. The first is multi-layer perceptron and LabGBM and range regression. With a linear regression meta learner, we trained this on about 10,000 synthetically generated outer care dialogue samples. The model predicts 4 emotion dimensions: anger, sadness, joy, and emotional intensity.
Intelligence fills text and speech signal, and we're using adaptive waiting technology. And when text is details and audio is unclear, then the text takes precedence. So the other situation is when the speech is processed but is brief, the speech takes precedence. So our system balance input based on 3 factors: text coherence, audio quality, and emotions. The confidence going about conflicting interpretations, especially important for mixed signal and for example, like mix of lover and tears. So this ensures consistent segment assessment.
And our strategy selector uses a layer hierarchical approach to choose the optimal responses for users. Layer 1 handles keyword alerts for crisis intervention, and Layer 2 provides early warning through sustained sadness detection. Layer 3 applied emotion-based rules for joy, anger, mixed, or neutral responses. Layer 4 just offered a fallback mechanism for other cases. And combined with additional features like RG and conversation history, the system generates contextually appropriate prompts and generates the response.
Here is how our early warning works. We watch for 3 straight sessions with high sadness, LIWC negative emotion, a shift from the baseline or crisis keyword. If something is flagged, we offer a brief GDS 15 to check in, such as caregiver contact, keep it optional, and protect data. Next page. Here is our long-term trend view feature. Each line is a signal we track across days, like sadness, social engagement, and overall sentiment. We look for sustained shifts rather than one-off spikes. If a trigger is hit, it shows up in the warning statistics table with the date and counts. In this sample, everything stayed below the threshold, so no warnings.
So our three-layer profile system blends personalization with privacy. There are 3 layers: layer 1, layer 2, and layer 3. Layer 1 collect essential registration data, some personal name, age, and household structure. And layer 2 offer optional details like health study and hobbies. And layer 3 is automatically track conversation partner and emotion trend early warnings. So all sensitive data is encrypted and the user remain full control of their information, which is allowing with strictly privacy by design principles. So next is our login screens. In left-hand side, the login screen use clear question, conditional field, and simplicity. The main interface feature voice, text, door model input. So the key functions are one-step accessible. Emotion trend will be questionnaires and the chat history. And it is designed for senior, like high contrast color, large button, and immediate income. So especially note the persistent microphone option for low literacy users. So next is this is our profile dashboard. The profile dashboard organizes data into 3 sections. They are personal information, family relationships, and lifestyle hobbies. The early warning static panel highlights crisis keyword a lot to the persistent sadness detection. So the interactive mode chart below translates mental health data to visual trend, and all are age-friendly designs like minimal scoring, large font.
You guys are way over 5 minutes. Can you wrap things up?
Yeah, for sure. And we also have some key limitations and the roadmap, which is skip those. And that's all for our presentations and any questions.
Okay, thank you. Thank you. All right, we have time for a quick question, perhaps.
It was not clear how you tested it. Did you test it on yourself, or did you actually get other subjects to test it?
For that question, I think we don't have real users. We just test it on ourselves and see if there are errors or bugs. Yeah.
Okay, and the data set you had, yeah. Okay, great. Thank you. In the interest of time, let's move on to Jiaozhang and Yoyu.
Hi, can you guys hear me?
You're sharing your screen, okay?
Yeah, okay. Let me share my screen.
Go ahead, yeah. Okay,
So, yeah.
looks good. Yeah, make sure you hit play, yeah.
Yeah, I'm timing myself. Yeah.
Great.
Okay. So
Thanks.
hi everybody. Today I'm presenting for my group. Our project is Mata, which is a new unified automatic calendar agent. My name is Yu Wu, and my partner's name is Zhao Mo. Let's face it, managing schedule information nowadays is still a hard task. I believe we have faced situations where we'll have to switch between different apps and manually input all the information. And we think there has to be a better solution than that. So I think we can formalize the problem of schedule management. Data from different sources will be stored into your brain or LLMs, and they can then process and integrate them into a comprehensive schedule. Seems to me to be a well-defined machine task, but why don't we have a solution yet? Turns out privacy is the biggest concern here because personal information are sensitive by nature. Popular calendar options usually implement using cloud solutions, and people don't feel comfortable letting big companies manipulate their data freely. The second problem is information extraction accuracy, because if an agent is to handle all your schedule information, it better achieve 100% accuracy, because otherwise most people just handle themselves because they would rather spend more time than missing deadlines. We also suffer from LLM response accuracy because LLM has illusions of thinking. It makes up wrong information. Simple tasks like what's due this week is actually much harder than it sounds. The reason for that is because LLMs don't actually store information in themselves. We have to use techniques like knowledge graph, RAG systems, or even MCP servers to achieve this. And we have to find the optimized way for our own project. So based on these analysis, we have developed the design principles of our project, which is the local architecture, a robust extraction pipeline, and the LLM planner with two calling function architecture for our LLM assistant. The first principle, local architecture. So basically, the processing of all the information never leaves your own computer. We have a local database, a local LLM server, and a local REST API server. So sensitive data never leaves your own computer. The second principle is a robust extraction pipeline. For each information source, we have a dedicated extractor, and after they are extracted, they are sent to the LLM parser for processing, and they are all processed into a unified JSON object. The third principle is the architecture of our in-app chat, which is LLM planner with two calling pipeline, because in this way we can ensure that all information presented to the user are accurate and not made up. So this is the high-level architecture of our project, a streamlined front-end and fast API server for communicating information, and Ollama local model, SQLite database, and Chroma vector database for RAG-based systems. The data flows in our system in this way. So plain text, canvas, all the information goes through the extractor, and the LLM passes them into a unified JSON object, and then stored into SQLite database, and indexed and stored into vector database, and used by the assistant. So here you can see some quick demos of our product. What you see here, why is not playing? So what you see here is a calendar filter with event details. When you click on them, you can see the details of the event, and you can also filter out the event types and names you want. The second one is, why it's not playing? I guess the video is not playing for some reason. So the second one is we have this sidebar for fast access. So basically in this sidebar, you can access the settings, you can input your own personal information. So it's convenient for the users. And also we have this in-app AI assistant. So basically you can ask any question to this assistant about your own schedule. So it will look up in the database in our design architecture and return you the answer. We also have an AI-generated digest functionality, which you can probably see here. So in this digest, you can filter out all the events type you want, and the AI will generate a digest for you. So this includes all the upcoming events that are filtered out. We also have a parse and ingest tag functionality. So basically, you can input any information you get from email or from PDFs or from other sources. So the LLM will automatically detect the information in these tags and then automatically store them into the database and inject them into the calendar. So that's it. To summarize, our main achievements for this project is a wholly local architecture to ensure privacy, a dedicated extractor to ensure information accuracy, and a carefully designed agent architecture using prompt engineering and other techniques to ensure LLM accuracy. We also designed a fast and efficient UI design using Streamlit. So future passes for project, we plan to have multiple profile management, or we also plan to integrate more data sources because currently we're restricted to emails and Canvas APIs. We also plan to fine-tune our LLMs using synthesized schedule information to achieve even better accuracy. And we also plan to use text messages or emails to send reminders to the users. Also, our code is open source on GitHub, so we welcome any suggestions or PRs for future collaborations. So that's it. Thank you very much.
Thank you. Questions? What is the accuracy? Do you have a sense of how good is it?
Yeah, I mean, we have tested with so we have several users for test, and we also try themselves. So
Okay.
basically, when you input like normal schedule information that's not too messy. By too messy, I mean like anything you can get from emails. So that's recognizable by human. It
Okay.
basically don't make mistakes, but we don't have like statistics for that. So just user experience.
Okay. I mean, it would be interesting to compare with what Apple does and I think other operating systems where, in your
Yeah.
emails, it suggests the calendar entries if it sees a date, et cetera, et cetera.
Yeah. I think the major competitiveness of our app is that it integrates sources that big companies don't have access to because
Right. Yeah.
users will likely trust a small company and it's open source. So it gives access to emails and Canvas APIs, and we
Right.
developed this like small pipeline very well for
Yeah.
efficiency, and user can manage them in the app. So I think that's the advantage of our app compared to them.
Right. I mean, definitely Canvas is interesting for students.
Yeah.
Yeah.
We also plan to integrate like Blackboard because other members in different schools use Blackboard, and yeah.
Blackboard. Yeah. Great. Thank you. We have Olivia, Paris, and Raina up next.
Hi there, everyone. Just give us a minute to share screen.
All right. Okay, we can see your slides. Yeah. Hit play. Yeah. Good. All right.
Welcome to our final symposium presentation. We're Raina.
Olivia Wong.
And so this is Navigate, a route analysis and navigation model for pedestrian safety using random forest algorithm. Navigate is a navigation tool which can determine the safest routes for pedestrian users in Boston. Existing models are focused on car-centric navigation routes and don't consider the unique needs of pedestrian users.
So what features are most important for pedestrian safety? Higher speed limits and crosswalk coverage are most directly correlated with crash risk. Higher speed limits are correlated with increased risk of fatality, while marked crosswalks reduce the risk of collisions at intersections.
Our literature review also reveals that better lighting conditions at night increases real and perceived safety of pedestrians, while street trees provide comforting shade and barriers. Factors such as sidewalk width, damaged slope, and existence of pedestrian ramps not only improve accessibility for those with mobility impairments, but also mitigate vehicular pedestrian crash risks.
So to give a high-level overview of this process, given a user inputted point A to point B, we generate 3 routes using Open Route Service API and detect safety features along these routes using the Analyze Boston datasets. We then feed these flagged features and routes into a random forest algorithm to determine crash risk. We display these routes and flag features to the user, ranking the routes in order of lowest route score.
So we use a random forest classifier, which is a collection of decision trees that is well suited for classification problems, handles nonlinear relationships effectively, and provides interpretable feature importance. For our data, we labeled a random set of 300K points around Boston using the Vision Zero crash dataset, separated by night and day crashes, then added the rest of our safety feature data and balanced the crash and no crash. We split the data into 80% training and 20% validation, and used a five-fold cross-validation on the training set. Both the nighttime and daytime model achieved an average accuracy of 94%, with a 4% mean difference between training and validation, and a 94% for holdout accuracy. Our confusion matrix showed good results in both day and night data sets with high numbers in true positive and true negative. Additionally, false positives are higher than false negatives, which is a safer direction than missing real crashes. Both our models perform similarly well with the area under the curve ROC of 0.99, meaning our model can almost perfectly separate crashes from non-crashes. Our precision is also very high, meaning our crash labels are almost always correct. This is supported by a predicted probability density, where we can see two peaks at 0 and 1 with minimal overlap between the blue and red bars, meaning highlighting our model's near perfect separation.
These graphs show the relative feature importance in the random forest models. As expected, speed limit is the most important, while indirect features such as tree, frequency, and lighting hold less weight, results which are aligned with accident analysis research.
Our model learning curve shows a small gap between training at our sample size, meaning the model is learning patterns. We also performed a permutation test, which yielded close to random accuracy as expected, confirming the model isn't just memorizing noise.
Here is a quick demonstration of our app interface. After typing in your starting and ending points, 3 suggested routes are generated, with the respective distance, duration, and route scores for each shown below.
For each route, we identify flagged features related to pedestrian safety and accessibility, such as damage, steep slope, nearby crosswalks, and more, color-coded for easier interpretation. Depending on the time of day, there are also flags for lighting conditions, which is factored into the route score at night. We allow the user to adjust the type of map view and to filter for the safety features that are most relevant for them to clear up visual clutter and prioritize preferred features.
As you can see in the side-by-side comparison of Navigate and other navigation apps, other apps rank Route 3 first, prioritizing the quickest route, while our model ranks it last because it has a relatively higher crash risk.
For further research and application, we could improve our current model by generating our own routes using the weight rather than relying on pre-existing APIs.
Furthermore, we could fine-tune our route comparison algorithm according to different user preferences and needs.
Our app also highlights regions with poor pedestrian infrastructure, which can be used to inform equitable urban investment in government policies.
Thank you so much for listening.
Thank you. Questions?
I'm just curious if you considered allowing people who actually used your app and to then give you feedback on how well they thought your app predicted what that route would be like from their point of view.
Yeah, that's a really great suggestion. I think having like user testers of the app would be a really great idea, but we just didn't have enough time to actually do that.
Okay, next step, yeah.
Yeah.
Good, other questions? How much effort would it be to train it for another city?
I think the greatest hurdle would probably be getting good and accurate data, because Boston provided pretty good data sets on all the features that we needed. So that's definitely a big hurdle we would need to get past. But
Yeah, we would like to have it in Portland. All right, great. Thank you again. We're a little late, but Eleanor is our last speaker in this session.
Okay, give me 1 sec to pull this up. Okay.
All right.
Hold on, sorry, it's giving me like 500 things. All right, I gotta keep it not full screen, otherwise it won't let me play the video.
That's fine. Yeah.
Okay, hi. This summer, I worked on exploring if spiking neural networks can be effectively used for audio deepfake detection. I'm sure everyone here has heard at least a whisper about deepfakes, which is any artificially generated media, so anything aside from text. The most common types of deepfakes that you may have heard of are images, video, and audio. This is an example of how deepfakes can be misused, and it's from NBC a couple months ago.
Value of voting Democratic when our votes count. It's important that you save your vote for the November election. We'll need your help in electing Democrats up and down the ticket.
So that is a clip from January of 2022, and it's a scam call using deepfake technology to impersonate former President Joe Biden. And the goal was to convince Democratic voters to skip the New Hampshire primary. It used characteristics of Biden's speech and was sent to thousands of voters, registered Republicans and Democrats alike. As artificial intelligence generators have evolved over the past few years, the presence of fabricated audio samples has grown significantly. Advanced foundation models are able to create samples that are too good for the human ear to detect. This poses a serious risk of breaches in people's security and privacy, like how we saw there, as well as the possibility of being weaponized to alter public perception and knowledge. As of a study in 2023, humans were only able to correctly identify deepfake audio clips 73% of the time. Since then, the generative technology has drastically improved. A more recent study shows only 50.57% accuracy in classifying audio samples. And while this number doesn't automatically appear to be that much worse, an average of 50% means that the participants in the study were largely guessing. The high standard deviation of 10.38% indicates lower reliability, supporting the theory that the results were simply guesses. This graph demonstrates the increased number of deepfake incidents in the past 8 years, and it's only considering the incidents that have been reported. Incidents are defined as public misinformation, defamation, fraud, exploitation, and identity theft. Now, there are two main methods for audio generation: text-to-speech and voice conversion. Text-to-speech is completely generated, doing exactly as the name suggests. Voice conversion is considered to only be partially fake, however. It's when you take the origin voice and keep their words, but change the tone or speaker of that to that of the target speaker. And these partially fake samples are the hardest to detect because many of their features are identical to those of real audio samples. Because of this, many effective deepfakes use a partially fake model, making them nearly impossible for detection algorithms to correctly identify. Here's a table from a comprehensive summary of what's been achieved so far in audio deepfake detection, written earlier this year. The table shows the performance of various algorithms that have been tested on the popular ASV spoof and ADT challenges. As you can see, the algorithm's EERs, which is the equal error rate, are high, up to 66%. The next step in AI development needs to be in an eco-friendly direction. As AI becomes more advanced, it also becomes more computationally complex and requires more energy. So, in order for detection methods to achieve their desired level of complexity and maintain their availability to the widespread audience of users they currently serve, there's a search for alternative options. One method suggested to achieve both computational and energetic efficiency is spiking neural networks, SNNs. As the SNNs only track spikes above a set threshold, they don't need to be constantly doing computations. They only begin to monitor a neuron after it generates a spike, resulting in a solely event-driven energy use. Also, SNNs are good for audio-oriented tasks as they're designed to have temporal inputs. So my goal for the summer was to create an SNN that can correctly identify if an audio sample is real or has been artificially generated. To my knowledge, only one other person has done this before and actually published a paper on it. It proposes two SNNs, when one is a hybrid convolutional SNN for both fully and partially fabricated audio sample detection. The author directly trained the SNN rather than the approach I picked, which was to start with a basic feed-forward ANN. It's much easier to train an ANN than an SNN so that it can learn through backpropagation, and I trained the FFNN on two popularly used datasets, the Faker Real and ASV Spoof 2019. And then I used SNN Torch to do the conversion to an SNN. Unfortunately, my results weren't very conclusive or complete. my algorithm couldn't reach any higher accuracy than 50%. So even though it had low loss values, it was really only guessing. Fundamentally, something was wrong with it because although other algorithms have been struggling to reach high accuracy marks, they've still been performing better than random guesses. So my next step is to get an algorithm to work, or at least do better than guess. And then, as I mentioned earlier, if the algorithm performs well enough, I plan to make it available to the public. So to give a quick demonstration of how this would work, I created a mock website. As you can see, it's a relatively simple design. The user can upload the audio clip that they want to verify here, and it will run through the program, and then the verdict, real or fake, will appear in this box here. I would give you a demonstration, but the algorithm runs too slow for the 15 seconds of time that I have on this slide. And although I do plan to finish the project, it is worth noting that with the continued development and widespread adoption of foundation models since the release of ChatGPT 4 in 2023, AI audio generated by AI audio detection research is increasingly focused on how to use foundation models to detect audio generated by foundation models. So for example, there's a new data set called Sonar that's being used to train and test foundation model detection methods. And traditional models like the ANN and the SNNI research will continue to inform future research on the use and foundation models, on the use of foundation models in audio detection. So yeah, that's all I've got. Thanks for sticking with me through that. And that's the gist of what I did this summer, and I'm happy to answer any questions.
Thank you. Questions? Quick question. Why do you think the problem is so hard?
For the algorithms to do
For
it.
the algorithm. I mean, it's hard for humans, and it's even harder for algorithms, or maybe
Yeah,
not.
I think
right?
it's because, so from what I was reading, it's because the features are so similar that even if it's like the level of feature extraction that it has to do is really high,
Mhm.
and it has to be like very specific, and not many algorithms are able to like reach that level of specificity needed for this.
Yeah.
So even if it's pulling like various features, it's still like the chances of it getting it wrong are still too high because the features of the fake and the real data sets are still like super similar.
Yeah. It's a really hard problem, yeah. All right, good. We blew through the break. That's okay. Feel free to drop off and take your own breaks. We'll move right on into our second session with Naomi.
Right, okay.
And Naomi's mentor was Surisha Kuturi.
All right, can you guys see this?
Yep, perfect.
All right, let me set up the.
Good.
Okay, so this is my project, improving pedestrian count estimation with machine learning and data fusion. My mentor was Dr. Koturi, sorry. So I'll start with an introduction. Pedestrian volume data and estimation is pretty useful. It helps inform urban planners on stuff like the development of safety measures, infrastructure, etc. So for example, data is typically measured at intersections with automatic or manual counters. For manual ones, we would just send out someone to at an intersection to like check pedestrians. Automatic is like a device, a permanent device that does this. Both forms of these counters have their downsides, namely the cost and scalability. So as you can see from this map, this is counter sites in Portland. The coverage isn't excellent. So there's a need for more convenient ways to model this. So Strava is a fitness app. It's often used by people as an activity tracker for like their runs and walks, etc. Previous work was done by my mentor and colleagues using this data to model pedestrian counts. So my goal basically is to apply some machine learning techniques to hopefully improve pedestrian count models. The data I'm working with has three main components, Strava, static, and count data. The count data is pretty self-explanatory. The static data is stuff like sociodemographic and environmental variables, like say for example, the median income of households surrounding the intersection. So I initially tried using XGBoost, feed-forward neural network, ElasticNet, and also support vector regression. I wrote my code in Python. So first I split the code into a train test split of 80-20. I used fivefold cross-validation to tune hyperparameters and then trained on the full training set and calculated performance measures on the final test set. So these are some preliminary results. At first glance, this looks pretty good. However, I realized that the performance of models was pretty heavily dependent on the specific data included in the train and test splits. So for example, these are some predicted versus actual value scatter plots across 4 random splits. As you can see, the performance varies quite a bit. And interestingly, the best performance outcome happened when the model wasn't evaluated on high count data. So to alleviate this, I used a leave one out cross validation for a more stable and unbiased measure of performance. Basically training 101 models on 100 data points and leaving them out. I also did some feature selection using ElasticNet because basically it regularizes some of the coefficients of variables down to 0, so it's useful in that regard. And I also got feature importance from a light GBM model, which is like a tree-based model. And it's measured by gain, which is basically like the improvement in performance that the model got from using a specific feature in a split. And so here's some here are my results. I decided to go with CatBoost and Random Forest now instead of the feed-forward neural network and SVR because those two consistently performed much worse than the XGBoost. So this is a scatter plot for the residuals versus actual values for CatBoost and the baseline negative binomial regression. As you can see, they both generally follow a similar trend. And this is a bar chart of performance across binned actual counts. So it seems that both the CatBoost and random forest models methods generalize a bit better to like higher count data. So basically it seems that like this is a graph of the mean absolute percentage error per bin of actual totals. So it seems that there's like a trade-off between accuracy in the low counts versus high counts. So the data set was pretty small. There was only like 101 total data points. In general, it is more important for a model to perform better in high count areas, which suggests to me that the random forest and CatBoost methods tended to be slightly better. And I think with more data, perhaps from like other cities, performance could be boosted quite a bit. I also like to thank the mentor, Dr. Koteri, Joseph Broach, who did a lot of the original modeling, and also, of course, Dr. Tusher. All right, thank you.
Thank you. Questions for Naomi? You had one, I think it was slide 13. Speed was the top ranked. Was that speed?
Oh, yeah.
Speed of what? Speed of.
Oh, it's like the speed limit of like the
Oh,
surrounding
the
road.
speed limit. I see. I see. I was thinking speed.
Yeah, that
of
intuitively
pedestrian.
makes sense to me because like, if there's a very high speed limit road, then it's not very safe for pedestrians.
Yeah. Okay, that makes sense. Yeah. Okay, cool. Good. Other questions? Great. Thank you, Naomi. We have up next Andrew and Robert.
Okay. Do you guys see this?
Not quite yet, but yeah,
okay.
now we can.
Okay.
Good.
I'll wait for my partner Robert to be ready. Okay.
Yeah, I'm ready. Okay. Okay, so my name is Robert. My partner here is Andrew, and we're electrical engineering students at UAC, and we're here to solve a problem that every student faces, finding the right spot on campus without wasting time.
We can hardly hear you. Can you speak up a bit?
Can you hear me better?
Not really, but it's okay. Speak up as much as you can.
Okay, sorry. So our problem is students waste precious minutes, sometimes hours, just trying to search for a study or hangout spot. For us, we've walked into our library or other study spots many times and found it either packed with no seats or too noisy to study in. Current tools give basic info like opening hours or head counts, but they don't really tell you what the place feels like. They don't really tell you if it's bright or dim, clean or messy, or whether a lot of people are working solo or chatting in groups.
Our solution is PrimeTime. PrimeTime is a mobile app that crowdsources real-time qualitative descriptions of campus spaces and tells users not just how crowded a place is, but what it actually feels like to be there. Built for students just like us who don't want to waste more time. So, how does our app work? PrimeTime collects voluntary student feedback using sliders and REU buttons, stores and analyzes the data, and displays spaces on a live campus map with scores for qualities and gives you the current purpose of the place. So, why college students? Well, for one, we're both rising sophomores in college. We're also focused on college students because they're highly mobile, more willing to share quick feedback, and campuses have constant traffic, making data fresh and more likely to be updated real time.
So here's an example of our map interface. The blue lines indicate where people usually walk, and the red pins are where we would call the busy areas where people tend to be. And when you click on them, they bring you to the report page.
Okay, so after clicking on a location, users interact with 4 sliders for measurable traits: noise, crowdedness, cleanliness, and temperature to help describe location. Then they use the 5 radio buttons to identify the general purpose of the place.
Speed and simplicity matter. If reporting takes too long, people won't do it. That's why we prioritize prime time to be as simple and effective as possible. A single sheet with sliders or taps you can complete in under 15 seconds. The simpler it is, the more data we can get, and the more accurate our data becomes.
Okay, so here's an example. A student might walk into the library and submit a noise of a 2, crowdedness of a 5, cleanliness 9, temperature 2, with the purpose of studying. Now that data is stored in our database and used to generate a description of the location. So, as you can see, the app outputs ratings on our previously mentioned attributes and main purpose for the library. In the previous slide, you can see that there is some difference between the user input and display result, such as noise being a 1 instead of a 2. So this is because we have set in a bunch of dummy data values with what we think a place is in order for our locations to not be easily skewed by bad input. So for now, I have set around 100 inputs for each location. And the hope in the future is that crowdsourced data from students will make the results stay pretty accurate. Flow is simple. Students submit 5 stories in our database and our app updates instantly. And then within seconds, anyone on campus can see the ratings of a certain location.
For students, the immediate benefit would be the time they save as well as the stress they avoid. They would not need to waste time/effort looking for their preferred spaces and instead could scout ahead without even leaving their desk. And on the other hand, for universities, they can gain insight on how their facilities are being used, helping with future space management, and thus giving them data on where their students would like to go.
Okay, so the majority of our work we had to do was a bunch of coding, and that was done mostly on Flutter using Dart. And for collecting and storing data, we use Firestore by Google. And then for the map, we use Google Maps API to start with our work.
Currently, we still have some challenges we have left. One of them was a big issue with malicious data. We've been able to eliminate like small inputs that skew our data, but with severe efforts to change it, we still have that problem. And we also have another problem with keeping enough users to keep our data fresh all the time.
Okay, in the very future, we plan to actually implement this app into our campus first. And then after that, we hope to expand to other universities across the United States. So Also, there's some future features we hope to implement that we didn't get to this summer. To start, we like to make a working comment section for users, maybe like a comment section where they can upvote and downvote, and a feature that takes the time and events of certain events on campus into account.
So thank you all for listening to our presentation. And this is the prime time to join prime time.
Thank you. Okay, questions for Robert and Andrew. So it seems a user can easily. Oh, Roberto, go ahead. Yeah.
I was just gonna ask, it seems like you guys are relying pretty heavily on users to report, right?
Yeah.
Have you guys thought of any solutions that might be able to kind of get around that? Like a temperature, for example, is something that can be like kind of gathered remotely. Noise level also possibly something you could gather without user input. Cleanliness would be difficult to do, but I feel like there's room to kind of automate some of those things so that you have more consistent and accurate data. But have you guys thought about that at all?
About heat maps and that kind of stuff, but that we also thought was like, what if there's a lot of heat in one area and it's not really like people. Like we did think about it, but um that could also be a thing that can make our product a little better. Yeah.
Yeah, overall, I think it's an interesting idea. It's just that it would definitely be hard to have it up and running based solely on user input, you know.
Yeah.
All right, thank you. Let's move on to Daniel. Okay, see your slides, yep.
Okay, there we go. I'm just going to set up my 15-second auto advance.
Great.
Oh, okay. Okay.
Perfect.
So hi, everybody. My name is Danielle, and today I'm going to be presenting my project, which was exploring adversarial attack detection methods for multimodal reinforcement learning agents, or RL agents. I'm just going to start off by quickly explaining some background information. So first, adversarial attacks are methods of introducing small changes to a model's input data, which then cause the model to behave in unexpected ways, often resulting in the model misclassifying or making incorrect predictions. Multimodal reinforcement learning agents combine different modes of input to make decisions, and they also learn through an exploration or trial and error approach. Currently, there is no existing literature that discusses their adversarial robustness, which is where my project comes in. So the objectives of my project were to evaluate detection as an adversarial defense, and also examine how attacks on different combinations of modalities may influence the effectiveness of attack detection. And basically how I did this was I attacked an RL agent on different combinations of its modalities. I collected its observation data, and then I explored classical and deep learning machine learning methods to detect adversarial examples in these different data sets. So to train my baseline RL agent, we use the soft actor critic algorithm in the Mujoko ant maze environment. This environment includes a 3D quadruped robot and a maze, and then the RL agent's goal is to navigate the ant from a start point to an end goal. The observation space of the agent consists of the ant's positional, angular, and velocity values for each of its joints. And this is basically just the information that the ant is using to decide the best actions to take. To attack our model, we use the fast gradient sign method, also known as FGSM. We use this to attack the observation space that I described before, and we attacked like different combinations to observe the unimodal attacks versus multimodal attacks. And then another thing we wanted to look into was the effect of scaling the attack intensity. So we looked at two different kind of levels of attack intensity, 0.007 and 0.015. So the different models that we looked into for detecting adversarial attacks included clustering methods, shallow classifiers, as well as neural network classifiers. The different clustering methods that we used included k-means and Gaussian mixture models, or GMM models. For the shallow classifiers, we looked into k-nearest neighbors and support vector machines. And then finally, for our neural network classifiers, we looked into fully connected neural networks as well as convolutional neural networks. To evaluate our models, we used the F1 score and the detection accuracy. In doing this, we found that the classifiers performed better overall than the clustering methods. We also saw that the angular attacks in most cases were more detectable than velocity attacks. We also saw that for some detectors, scaling the epsilon value led to a significant increase in detectability. And then lastly, we noted that the fully connected neural network performed the best out of all of the different models that we were looking at. So with the FCN model being the best performing detector, we conducted feature importance analysis using SHAP and feature permutation. I found that the best performing FCN model showed a strong skew in importance towards angular modalities, as you can see here. And in contrast, I saw that the worst performing FCN model attributed most of its importance to velocity and position of the torso. So that yielded an accuracy of 54.94%. So here are some key takeaways and implications from my findings. First, I found that there's a disproportionate effect of different attacks on different modalities, as angular values were more telling of adversarial perturbation than velocity values. I also saw that stronger attacks were significantly more detectable, which forces adversaries to strike a balance between impact on model performance and detectability. Next, I'll go on to describe some future work that we could look into. So one thing that my project didn't look into was detection as an active defense. In this case, we would have to consider things like the evolution of attacks, the variety of currently existing attacks, as well as the time and resource efficiency of the models used. And then another area of future research could include looking into attacks on other aspects of the Markov decision process, for example, the reward function and the action space of a reinforcement learning agent. So that pretty much concludes my presentation. I just wanted to say thank you to my mentors, Shayan and Dr. Akabdar, for their support and guidance throughout this project. It was a lot of fun to work with you, and I learned a lot throughout this summer. So thank you.
Thank you. Questions for Daniel? All your models were feed-forward stateless models, right?
Yes.
Is that correct? Would adding, a recurrent model add to the performance, you think, or to the accuracy?
That isn't something that I considered, but it is definitely something that I could look into. Yeah, I'm not sure though.
Yeah, interesting. I mean, maybe because you have a reinforcement learning loop, maybe the recurrency doesn't actually add because you already have a state in your system implicitly. I'm not sure. Something to think about, yeah. Good. Any other question for Daniel? All right. If not, we're moving on to Abby and Adavit. Thank you, Daniel.
Can you see my screen?
Yep. Okay, good.
Cool. So this is our final altREU presentation. Our project is called YieldQuant. My name is Advait.
My name is Abi. All right, so talking about the project goals, the goals were to build a Bayesian yield curve for certain municipal bonds across different sectors, quantify the risk and uncertainty in the yield prices for investors, and also help municipal corporations to target improvement for certain bonds.
Okay, so first of all, I just wanted to go over why we're doing Bayesian instead of polynomial. So for polynomial regression, it's just very simple. It gives less information and it generalizes the overall pattern. But Bayesian, on the other hand, shows uncertainty. It shows a full posterior distribution and it captures smaller patterns as well.
And as you can see here in the polynomial regression plot, I mean, it's just a scatter plot. You have plotted some points from the data and you just join them, and that's a linear, it's a line graph, you can say, where you're plotting the yield versus bond length. There isn't any more analysis done on this.
So our approach was to use an RBF kernel, after that fit the Gaussian process regressor, and then finally plot the posterior samples.
And yeah, the one quantity when we talk about relationships using Bayesian yield curves is the negative log predictive density, which is NLPD, and it predicts how well the data is predicted, how well the data matches the model. And the lower the value, the better. And for the Portland affordable housing bond, the NLPD was minus 1.13, which is good.
And this is the graph for the Portland affordable housing. So this is the Bayesian model which we fit, and here you can see the NLPD is pretty low, so that's good. The pink X's show the excluded test points, which kind of show how good our model did in predicting.
And then this is the Bayesian model for the Portland Veteran Memorial. And as you can see here, there's the 95% confidence interval is really broad. So there's a lot of uncertainty in this model.
And this is another model which we fit. So this is for the Katy Independent School District bonds. Here, one thing we can notice is that the bands are pretty thin, so there's very less uncertainty surrounding these bonds and their yields. And another thing I wanted to point out is the lines are like sampled functions, so they're basically like possible or plausible functions that could basically give you the function for the line of best fit.
And then this is the bond length versus yield for the Austin Independent School District, gradually increasing at the beginning, but gradually decreasing, showing similar trends with the affordable housing bond.
And then this was another data visualization we did. This basically shows the posterior yield distributions at selected bond lengths for the Austin Independent School District bonds. So as you can see, the one on the left is for 5 years, then the middle one is 15, and the last one is 20. And it really just shows us like for different bond lengths, how much the variability, like the standard deviation increases or decreases, and the uncertainty surrounding it.
And then here we did a cross-sector analysis with the same city. So for Portland, we chose the affordable housing bond and the veteran memorial bond, and we put both the Bayesian models onto one plot. And as you can see, the veteran memorial has significantly higher yields throughout different bond lengths, and which shows that this municipal sector is performing a lot better than the affordable housing bond.
And then we also did some cross-city analysis. So we chose municipal bonds from Austin and Katy for the independent school district. So we kept that the same but changed the city. And here we can also see some interesting comparisons. So around like 0 to 5 years, the predicted yields are pretty similar, but after that, Austin's are much higher.
And when we did the comparison, we put two Bayesian models onto one graph to do better analysis and better comparison across different bonds. And then, of course, we do see differences in yield rates change depending on the length of the bond. And what we saw is that the longer the bond length, the higher is the yield rate. So generally, there is a positive trend there's a positive relationship between the bond length and the yield rates.
And then this was the posterior yield distributions for the cross-city analysis we did. So we just chose for 5-year bonds, and we can see how Austin's yield is overall predicted to be less, but there's a slightly higher standard deviation, so there's more uncertainties surrounding it compared to Katy's bonds.
It's the same thing here, but except the bond length is 8 years. And again, not much difference in the standard deviation. In this case, it's almost similar. But you can see that Katy's yield rate is overall much higher. And yeah, that's why it shifted to the right.
So it's just some challenges we faced quickly. One of them was finding the exact same sectors across cities. And then we also had to face overfitting and underfitting and just making sure we optimize the parameters correctly.
And then for improvements, we could definitely account for macroeconomic events. And we could have done some more additional data visualizations to help convince investors. And we could have implemented an enhanced user interface or dashboard.
And just quickly, the impact. So we wanted to reduce the risk for investors, have more investment in municipal bonds. I also highlight weaker bonds for targeted improvements, and also have advanced modeling, which can foster future prediction.
Thank you so much.
Thank you. Questions? Questions for Abby and out of it. Is the tool already available online for others to use, or do you have a plan to do that?
Yeah, we're planning on doing that. So we haven't made like an interactive user interface, so to say.
Okay.
It's just still in our like Jupyter notebook, but we plan to make it like available for like other people so they can just like choose a data set and then get it to work.
Yeah, that would be cool. That could be very useful. Yeah. Great.
Yeah.
All right. Thank you. We have Roberto next up.
Yo. Can you all see that?
Yep.
All right, let me set up my timer. Okay. So, hello, I'm Roberto, and today I'll be going over my work in ecosystem-based spatial validation of machine learning models for global plant transpiration prediction. And for that, we'll start off by talking about SatFlow, then we'll move on to SatFlexNet, ecological clustering, and others. For those who are unfamiliar, SatFlow is a process through which moisture travels through the roots of a plant up through the stem and out to the stomata. This transpiration process is also how plants exchange carbon dioxide with the atmosphere. Now, the data for this project comes from SatFlexNet. SatFlexNet is an initiative to compile and curate a global data set of sat flow measurements in plants led by researchers at CREAF. The SatFlexNet contains 165 sites and 23 years worth of data. Now, not all 165 sites are eligible for this project. The 87 sites that are eligible can be seen plotted here on this map. The sites cover a wide range of global area with a high site concentration in eastern US, Western Europe, and Australia. To work with SatFlexNet, we developed a pipeline that takes the raw data and transforms it into something that is usable by XGBoost. The general steps in this pipeline are the preprocessing of data, feature engineering, clustering of individual sites, model training, and cross-validation. Our first step is to combine information from various SatFlexNet sources into site-specific files. Each site has readings for several plants and environmental data taken at regular time intervals. We also have site-specific metadata files with our own useful features. We join the sat flow measurements from individual plants to the relevant environmental measurements and the site metadata. The end result is a single row of data for each measurement with all the context that surrounds it, which is ideal for XGBoost. We develop separate data sets to help investigate the effects of certain features on our models. Our default scheme includes data found in the source material itself. The ecological set adds extra derived features to the default set, and the comprehensive adds engineered temporal features to that. Once we process our data, we begin by clustering using a variety of algorithms. By taking into consideration silhouette score, balance score, and the overall final score for each number of clusters, we can pinpoint which algorithm and size to use for our models. This geographic clustering uses latitude and longitude as the only clustering features and produces clusters with concentrated silhouettes. However, there are a few sites here that are still far from the cluster center. Here we can see how those clusters apply to our sites on the world map. If you look closely, you might notice that geographic clustering sometimes puts distant sites in the same cluster. This result is something that ends up driving many of the outliers in our work and is difficult to account for. Once we have our cluster assignments, we can start training our baseline models. Here we produce a simple 80-20 split of each cluster's total data. We consistently see that these models produce accurate predictions, with R-squared values in the 90s being common. In these models, we found that datasets with temporal and ecological features improve the overall accuracy of our XGBoost models. Models trained on default data scored in the 80 to 85 range of R-squared values, while those trained on comprehensive data scored in the 90 to 95 range. Random split models are fine as baselines, but to test generalization across sites, we needed a different approach. We tested our model's ability to generalize on unseen sites by using leave one site out validation, or LOSO. The way leave one site out validation works is we take all of the sites in a cluster and separate out one. Then we train on the remaining sites and test on the final excluded site. This process is repeated for every site in the cluster, and the metrics for each fold are averaged. The results of leave one site out validation were starkly different from those of the cluster models. In these figures, we can see that this validation produces a wide range of results, with many of them being negative. As such, the average performance for these validations is also negative. You may be wondering why we're only looking at geographic clustering. We've had a number of clustering feature sets, but on average, other clustering methods performed worse. Climate clustering performed fairly well in some cases, but more often than not, clusters had poor silhouettes. The main issue is domain shift, or when training data is too different from our test data. Our clusters are so large that unrelated sites end up in the same cluster. Here we can see that the clusters we're looking at stray far from the mean soil water content in their overall cluster. The cluster distribution of sites on this map has been adjusted to reduce the amount of domain shifted soil moisture. However, this has resulted in clusters that span the globe and various biomes. This contributes to uneven model performance. The main conclusion here is that predictive accuracy from 80-20 splits does not transfer to cross-site generalization. Clustering improves within site predictive accuracy, but the strongest predictors of transpiration shift according to environmental pressures. As such, avoiding a domain shift in the future will require more data and careful management. And I didn't add a slide thanking my mentor, but I do want to acknowledge all the help that Dr. Hartzell gave me and all the freedom she allowed me to pursue in this work. And yeah, that's about it.
Thank you, Roberto. Questions for Roberto? Did you compare with another state-of-the-art approach, or did I miss that?
You mean a different type of model?
Yeah, a different type of model.
I did not, but I do know that previously other similar attempts have used random forest and have largely come up with the same results in terms of, at the very least, random split models. In terms of spatial validation, as I tried to do, it's fairly new. It's a fairly new approach to this work entirely. And as much as I wanted to employ another method, I ended up largely running out of time, but also did my best to exhaust every avenue with the model that I currently had to make sure that it was actually the model, or rather that it wasn't the model, but rather a consequence of the data. Partially because my mentors and others had suggested to me that actually the model has never been the issue, it's always been the data. The data itself, it varies widely from site to site. Overall, it's like incomplete in most sites, and then other sites have so much data that it dominates the entire model, right? So managing that is really where the work is at, and it's difficult because, like I said previously, everything shifts depending on the site and the interactions between features at every individual site. So coming up with a generalizable model is hard.
Yeah. Okay. Great. Thank you. Okay, let's move on to Louise. And his mentor was John Lepore.
Yep. In the Earth's crust, heat moves in mainly two ways. Conductively, where heat diffuses slowly through rock, and convectively, where heat is carried more rapidly through by water through faults, usually upwards towards the surface. A well is basically a deep hole where people drill. Usually it's a few miles deep. When a well is dug and its measured heat value differs significantly from expected heat value, this is called the heat flow anomaly and may indicate naturally occurring hydrothermal systems. This is important because hydrothermal systems can be harnessed to build geothermal power plants, which are good alternatives to fossil fuels and provide clean, sustainable energy. A well is drilled, hot water is extracted, it becomes steam as it quickly depressurizes and powers a turbine. The main issue is most hydrothermal systems are blind or hidden, meaning there's no obvious surface features like geysers or springs. Unfortunately, we also can't just randomly drill everywhere since each well costs a few $1 million to drill. This is the main issue that Team Mordensky explored in 2022. Basically, they trained linear regression and XGBoost models to predict heat flow across a part of the Great Basin region in the western US. And specifically, they used data spanning the Ingenious region, the study region, which is depicted here. They used 16 geological features, and for their labels, they used actual measured heat flow from wells. Ultimately, the team had decent results, but noted that their XGBoost models had issues with class balance and suggested future attempts with ranked ordinal regression could be helpful. They had in particular trouble with accounting for very high heat signals. It was skewing the model. That's exactly the focus of my project, building a convolutional neural network that works with patch level ordinal regression to predict hydrothermal favorability. Fortunately, finding the ingenious datasets was fairly straightforward. Half of the features required resampling and others required more extensive processing. For instance, the conductive heat flow feature first had to be extracted and interpolated into a viable raster. It's depicted here after processing. I went with Z-score normalization for the features since that's what the team originally used. Some features appeared to be more dynamic than others from the first glance. When it comes to patch creation, I created 900 patches with size 64 and stride 32. Each patch is assigned one of 3 ordinal float values depending on the highest recorded heat well inside that patch. Low at 1.0, high at 3.0, and very high at 4.0. Research indicates that excluding intermediate 2.0 values is optimal. It was critical to create spatially separated training and validation patches to prevent data leakage. One of the many lessons I learned the hard way. Here's some visuals with my training, validation, and overlapping areas. And also because my patches had a natural 50% overlap, they ended up being something called Swiss cheese patches, where their features are zeroed out depending on overlap with validation areas. Here's an example of 4 features in 2 different patches. Initial results from my efficient net-based model without class weights showed a pretty bad validation loss in ordinal accuracy, with the most apparent issue being class imbalance. As you can see, predictions were heavily skewed towards low and high and away from very high. The interesting part is when I aggressively tuned the model with class weights, the class balance improved, but the model still wasn't learning well, as evidenced by basically all the metrics shown here. We'll touch back on this in a moment. From a combo of curiosity and time constraints, I performed inference on our unlabeled patches. On the left here is the resulting grid with patch predictions, and on the right are the actual patches. And then next up is a visual with the green correct and red incorrect patches, patch predictions in inference. We still see a poor accuracy with predicting the very high class at the mediocre ordinal accuracy of 38%. Unsurprisingly, I attempted to change our feature resolution from 500 meters to 1000 meters per pixel, but when I noticed patches were getting reduced by half and bin distribution being unnaturally skewed towards very high, I realized it wasn't worth it. The research also suggests that some features are more important or predictive than others. A potential improvement could be to simply omit the weaker features. We could, for example, try using only 3 to 8 of the stronger features. And I'd like to give a special thank you to Dr. Lepore, Dr. Tusher, and Crow for being extremely helpful, and to my fellow cohort for being resilient this summer. We may have not all had ideal results, but we picked up some useful research and machine learning skills. And now I'm open to questions.
Thank you, Luis. Questions? I wasn't sure at the end, you mentioned you reduced the pixel size. Did you mean the patch size? Is that the same?
Oh, no, that has to do with the resolution, apparently. Like each pixel in the image denotes like a certain amount of length, like area.
Okay.
And on the features,
Okay.
yeah, on the
Okay.
raster. And then,
Okay.
yeah.
But it seems the patch size may also affect your final result. Did you play with that as well?
Yeah, I had a patch size of 64. Initially I had a 128, and the
Okay.
model wasn't working quite as well. But reducing it to 64 did help a little bit. Reducing it down more to 32 would apparently, I forgot the exact reason, but it was suboptimal. So I decided not to, not to try
Okay.
it.
Okay, so 64 was like the sweet spot.
Yeah, for now.
Yeah, I see. Okay, cool. Other questions? All right, if not, we have Josiah and Myra in the session as the last speakers.
All right, can you hear me?
Yep, we can hear you.
Awesome. Let's see. Let me pull this up real quick. Sorry about this.
Okay, it's coming up. Yeah, great.
Okay. Um, okay, we're good to go.
Good.
Myra.
We can't hear you, Myra.
Hi everyone, my name is Maya Soloria. I'm the Josiah Library with fourth year students of State University studying computer science, and we're excited to present our project today, ClearText. So many people struggle with dense city notices, legal letters, healthcare documents, and our project aims to make these texts easier to read and understand for everyday readers, which is important for accessibility and inclusivity. Our target users are the general public, but also we focus on seniors, non-native speakers, and anyone who finds complex text difficult. We want to empower them to understand important information clearly so they can feel confident.
Yeah, so the main goals are to simplify text using a custom readability model and compare it to the Flesch-Kincaid model, highlight hard words with plain alternatives, and make documents accessible to more people. So we use the Flesch-Kincaid model to the Flesch-Kincaid formula to measure readability. It uses total words, sentences, and syllables to tell us an average grade level and reading ease of text. It gives us a score from 1 to 100, with 100 being the easiest to read. Our tool is built with Python and Flask for the backend, Spacey for advanced text analysis, and Deep Translator for multilingual support. The front end uses HTML, CSS, and JavaScript to handle user interaction.
Clear text can highlight parts of speech, calculate readability scores, identify complex or uncommon words, simplify the text for easier understanding, provide translations all in one easy to use interface. The workflow kind of goes with the user inputs text directly or uploads a PDF. The program is going to analyze it. It highlights key parts of speech and difficult words, simplifies the language, and then outputs a clear, easier to read version for the user. So as I mentioned, this is kind of what it looks like. There's two things that the user can do, either type or paste text directly into the program, which gives them flexibility for handling different materials that they might want to put in. Anything from like city letters to just other documents.
Yeah, so we calculate the percentage of common words in a text to measure its simplicity. This helps us understand how simple or complex the text is for readers and guides our simplification process to make the content easier and faster to read. For testing purposes, we use the simulated city notice as our example document. This allowed us to demonstrate the simplification process on a real-world example that residents are likely to encounter in their lives. And then we calculate several readability metrics, including the Flesch-Kincaid reading ease and grade level, average words per sentence, syllables per word, and total sentences and words. These metrics help our simplification strategy.
And then we also implemented parts of speech tagging. So we highlight things like nouns, verbs, adjectives, just different parts of speech, giving users visual cues about sentence structure, helping them understand the text better, and then also more for advanced readers who are looking to learn a bit more. And also highlight for definition. So as shown in the picture, users can highlight the words to see simple definitions. This reduces confusion, improves comprehension without changing the original meaning. So here you can see the example, the word corresponding. And then here's an example of the city notice mentioned earlier after simplification. You can see that complex words like the word correspondence went to letter, and the average grade level score when calculated on this went down from a college reading level to a fifth grade level.
Yeah, so we also provided a Spanish translation of the simplified text, making the tool accessible to non-English speakers. For this Spanish translation, it also went down from the initial college level rating to a fifth grade level reading. Some challenges that we faced early on were learning to protect our user privacy and data. We didn't want to keep any of the user data, finding users that matched our target audience for testing, and preserving the original meaning while also simplifying. To address these, we avoided storing any type of user data for privacy concerns. We conducted careful user testing with people who match our target audience, and we incrementally refined simplifications to maintain meaning.
In the future, we aim to continue improving the simplification engine for a larger dictionary capability, add more language supports to reach more users, and optimize the user interface as it's fairly simple and outdated looking at the moment. But we learned a lot while working in a team on this, conducting research on the existing simplification methods and formulas, and then designing a project from start to finish. We're excited to see where this continues to go, and we're happy to answer any questions.
Thank you. Questions? Mar. How do you make sure you're not oversimplifying? Is there a safety net in place there?
So currently the only placeholder for simplifying is it's going to simplify to a fifth grade reading level, based off of the metrics of the Flush-Kincaid formula and then the formula we also created.
I see.
Yeah. Yeah, we had an idea of like doing iterative simplifying where it would simplify down to like a certain level and then you could simplify it further and further. And so I guess that would kind of make it so that the users would have to determine whether or not it was too simplified. It would kind of put a bit of that burden on the users, which we ended up not implementing that yet, but it was an idea that we had.
Okay. But that would be really hard as a user, right?
Yeah.
Yeah. Okay, great. Thank you. Other questions? All right. If not, we are on break time. We have about 8 minutes until our next session starts at noon Pacific time with River. So feel free to drop off and come back, or you can just stay online. We won't quit the presentations here. So we'll see you all in 8 minutes. Thank you. All right, folks, welcome back. We have 2 more sessions. River is going to present as our next speaker. River, it seems you're ready. And River worked with Tammy Lee. River, you're muted.
Yep.
Okay, good.
Of course. Thank you. All right. Make sure I play. All right. Hello. I'll be presenting my project on comparing Ultralytics YOLO V8 and YOLO V10 for multimodal transportation counts. Quick definition, multimodal transportation is anything you would see on a sidewalk rather than driving on a street. First, why count non-car traffic? Well, there's been more interest in recent years in pedestrian-friendly design. In order to implement that design well, however, data on current usage trends needs to be collected. So here's the state of the art on methods for active transportation counts. Manual counts are the most common. Specialized devices are less labor-intensive and less versatile, and machine learning is what I focused on for my project. Manual counts are sending people out with clipboards and ideally video cameras. They can be accurate and they're very versatile in recording different types of traffic, but they're labor intensive and they can't be used for long-term counts. There are also very specialized devices available for active transportation counts. They can be used for long-term counts, but can be expensive to install and only distinguish between pedestrians and bicyclists at most. Object detection models can track and count pedestrians and video footage. For equipment, only a video camera is required, and it can be used for long-term counts. So in my project, I focus on improving the accuracy and versatility of this method. Specifically, in my project, I compare 2 versions of the Ultralytics YOLO model.
I used the EuroCity Persons dataset, which is a large image dataset for multimodal transportation detection. And YOLO is a single-stage object detection model. It stands for You Only Look Once. This means it's fast without sacrificing accuracy. It's a popular choice for similar model tasks, and it has many different versions to choose from. Specifically, YOLO v8 performs well overall and is established in research, but has difficulties identifying objects in crowded scenes. YOLO v10 is more complex, but in particular improves in identifying objects in less sample categories. The EuroCity Persons dataset has over 47,000 images taken at pedestrian crossings in other urban areas from 31 different cities in Europe. Pedestrians are the best represented category, with nearly 200,000 samples. There are 10,000 samples for bicyclists, 5,000 for scooters, and a mere 125 for wheelchair users. This is still better than many other datasets, unfortunately, which don't have wheelchair users included as a category at all. For data, I used a Python script written by Alicia Hopper to convert the ECP dataset image label files into a format that YOLO uses. I also used this script to exclude faraway and overly occluded bounding boxes. I used the small-sized pre-trained models for both YOLO versions. I initially tried training them for 300 epochs, but that ran into overtraining issues, so I continued with 200 epochs of training for my other experiments. Including only bounding boxes that were under 10% occluded led to the worst results for both versions of YOLO. Including every bounding box, regardless of level occlusion, was found to lead to worse results for YOLO v8 in earlier work, and it did for v10 as well. The precision of the model suffered especially. Including bounding boxes that were 0 to 40% included led to the best results for both versions. YOLO v8 had slightly better performance overall, especially for pedestrians and bicyclists. However, YOLO v10 achieved better results for categories with fewer samples, like wheelchair users. So, what's next for the project? Validation of the models against existing video data at intersections is a good way to test them in their intended use case, and was originally planned for this project, but I ran into the time constraints of the REU program. Hyperparameter tuning is a good way to improve model performance in general, but it was out of scope for this project. It also requires time and access to ideally multi-GPU resources. Lastly, based on the results from this project, using a custom dataset along with the ECP dataset should address the model's difficulty in identifying wheelchair users in particular. And finally, I'd like to thank you all for listening to this presentation. And if you have any questions, please ask them.
Thank you. Questions? I think you kind of answered my question, but I was wondering if, since the data set is pretty large, did you use GPUs in the cluster for training?
So, I did not use the GPUs in the cluster because I initially got set up with a different server, and by the time I realized I could have used the cluster computing, I was already wrapping up my experiments and writing up my results and everything.
Sure. Yeah. And I think you mentioned correctly, hyperparameter optimization would take even more time and is very compute intense. Yeah. Okay, good. So that will be future work. Yeah.
Yes.
Good. Other questions? Good. If not, thank you again. We're moving on to Youyang and Max.
Afternoon. Here, let me screen share real quick. Sorry.
Sounds good.
Awesome. There we go. Sorry about that. There we
Good.
go. All right.
Did you hit play? Oh.
Yeah. Good afternoon, everyone. My name is Yu Yang.
My name is Max. We're presenting on the Predictive Art and Painting tool, or Paint. Our goal is to help restore damaged artworks using AI while preserving the original style. Today, we'll walk you through why we built it, how it works, and what impact it can have.
Art is one of the most powerful ways we connect to history, culture, and human creativity. But over time, paintings fade, tear, or are damaged. Many of these works risk being lost to the public forever unless they're restored.
Art restoration today combines science and craftsmanship. Experts first assess a piece using imaging techniques such as X-rays and infrared to detect hidden damage. They then clean it with precise, non-invasive solutions, repair structural issues, and then finally retouch faded areas.
However, restoration is a slow and expensive process, and therefore not many art pieces are properly restored, and experts may rush the process, leading to results like this.
Paint is designed to assist restoration experts, not replace them. We want to give them a tool that can rapidly propose high-quality, style-accurate restorations so they can work faster and work on more pieces.
Unlike most AI art tools, Paint is style-aware. It doesn't just guess what is missing, it identifies the artistic movement and uses a specialized in-painting model trained for that style. This makes it far more faithful to the original artwork.
Our pipeline begins with our input image, which we detect the damage from. Then we classify the style of the artwork. We send both the image and the damage mask to a style-specific in-painting model. And finally, we output the restored piece.
We use CNNs for damage detection and style classification because they're efficient for spatial pattern recognition, while for in-painting, we use diffusion-based transformer models, which excel at generating high-fidelity textures and stylistic detail.
Our dataset comes from web scraping, museum archives, and open art datasets. We have around 25K artworks. We label each image by style and then generate synthetic masks to simulate different kinds of damage. This lets us train both the detection CNN and in-painting models efficiently.
Our first goal is to simulate damage on different artworks. We created a custom OpenCV function that would take a painting and apply flaking at different intensities, so we could train our CNN to detect damage and fine-tune in-painting models.
We started with a CNN that detects and masks the damaged regions of the painting. We used 4.2K damage artworks to train it, and used attention gates to focus on damaged regions, and used focal diversity loss to heavily penalize missed damage.
Next, we run the intact portions of the artwork through a simple CNN to classify into movements like Impressionism, Baroque, or Cubism. This classification step is critical because each style has unique color palettes, brushstrokes, and composition rules.
Our model was trained to take in a rescaled 2048 by 2048 image of the artwork, and we run it through 3 kernel layers and one final hidden neural network layer before classifying the result. We trained the model using an 80-20 split across 40K artworks.
After classification, each art movement is paired with the fine-tuned Stable Diffusion 1.5 model, a sort of expert trained specifically on that style. The model receives both the original image and the damage mask and fills in the missing areas with stylistically accurate content.
Here's what it looks like: the damage painting, the detected damage mask, and the final restoration. The model can recreate fine details while staying faithful to the original style.
We measure performance on the in-painting model using PSNR, or peak signal to noise ratio, with our average score being 19.49. For the classification and masking CNNs, we measure performance by evaluating the prediction accuracy rate for a result of 91% and 97.5% respectively.
Here are some before and after examples. You can see that the restored areas blend seamlessly with the original for certain paintings in certain areas. However, some experts don't perform as well. We can pin this large variance in performance due to the certain art styles have a more distinct style to them.
So as for impact, Paint can make restoration more accessible to smaller museums, archives, and private collections that don't have the budget for months of expert work. It's also a powerful educational tool for teaching art history and preservation.
The biggest risks are accuracy and authenticity. Without expert oversight, the AI could introduce incorrect details that alter the meaning of a piece. That's why we see Paint as an assistant, not as a replacement.
In the future, we could adapt Paint for other media like historical photographs, film frames, or even sculptures. Partnering with art historians could improve authenticity and trust in the tool.
In short, painting helps preserve the past using tools of the future. By combining damage detection, style classification, and style-specific inpainting, we can help restoration experts work faster and make cultural heritage more accessible. Thank you.
Yeah, thank you for listening. And we'll have up the some pictures of our we'll have up some of our pictures so you can see some of the results. And then this one too.
All right, thank you.
Yep.
Questions?
Thank you.
Did you run it through ChatGPT or any other LLM and basically ask it, well, can you fill in the gaps to see what happens?
We didn't. Oh, sorry. Yeah.
I mean, we experimented with Stable Diffusion 1.5 like prior to like choosing it as our inpainting model. The reason we did that is because Stable Diffusion 1.5 is considered relatively lightweight, but there are certain drawbacks that it has. For example, it's not super good at rendering like different like body parts. Like as you can see, like by like kind of like Mona Lisa's like weirdly shaped hand. It's also not the best at like doing text or like very fine intricate details, but like there are way more powerful stable diffusion models out there, but they just take like way more time and computational power to run. And we ran most of our code on a Google Colab with the Pro plan as it's free for students. So most of we use T4 GPUs and A100 GPUs for our training.
So it's still pretty compute intense.
Yeah.
Yeah, it would take us like a couple hours to be able to train like each model. So yeah.
Okay, cool. Anyway, I think it would still be interesting to compare, like, quantitatively with your metrics, how does ChatGPT or any other diffusion model do versus yours?
Yeah, and that would definitely be a next step of ours.
Yeah.
But we did just run into a lot of time constraints evaluating our models.
Yeah, good. Okay, cool. Other questions? All right, thank you. Brandon, up next.
Yeah. All right, I will share my screen and just get right into presenting.
Sounds good.
All right. Here we go. Okay. All right. Good afternoon, everyone. My name is Brandon Calvario. Today I'll be presenting my research on topological data analysis of Western United States power grids under wildfire disruptions. This was mostly about examining the resilience of power infrastructures through the use of topological data analysis and persistent homology. So, as we've known, the United States faces an unprecedented wildfire crisis. We are seeing more fires burn longer and destroying infrastructure. The question now isn't if the wildfires will hit the power grids, but it's when and how badly the result will be across not only the cities, but all of the counties nearby. But when a wildfire just takes out a few power grids, we also need to think about how many blackouts happen for all of the thousands of people and all of the miles away. We basically need to understand all of these vulnerabilities right before the disaster strike. So how would we do this? Well, I built this interactive tool that lets the user explore how wildfires impact power grids. You can select any Western state, any intensity from low to extreme, and see exactly how the electrical and infrastructure responds to wildfire attacks and data based on your selections. Apart from that, we also use topological data analysis or TDA. Think of it as creating mathematical fingerprints for the power grids. It is also used alongside the vectorial strips complex to track topological features, which reveals hidden patterns in networks through persistence diagrams that traditional methods usually miss. And for our Wasserstein distance, that is the method we used. And what it is it basically quantifies the structural damage and it measures the changes between the events. So a smaller number would mean minor repairs, but a larger number would basically mean major damage or even catastrophic system failures. For our data, we use the National Interagency Fire Center to source our data, as it is the most up-to-date source. It also contains fire parameters for the entire United States, which allows further development for other regions like the East. And for our power grid data, we are using the Actives 10K dataset, which is a synthetic but realistic 10,000 bus grid covering the Western United States. Every bus has real electrical parameters, coordinates, generation data, and it is also able to be used in the software Power World, which allows power flow visualizations. For my UI steps, You basically pick a state, you select the fire intensity and applies the filters you'd like, such as the fuel type that was burned in that fire. Then you're able to choose that event. And from there, you're able to analyze the power and impacts that the fire has. And for our sequence, the program identifies which power stations are directly hit by the fire. It identifies nearby vulnerable fires as well, or infrastructures, I mean. And finally, the program simulates the cascading failures that ripple throughout the entire grid. We also have the TDA sequence, which compares the before and after wildfire damage, and we basically create mathematical fingerprints of both states. We basically measure exactly how much the power system's fundamental structure has changed, but this also ties into an example that I would like to show, which was the Creek Fire, which is the sixth largest California fire in history, and it burned over 379,000 acres and destroyed nearly 1,000 buildings. The reason I chose this was because we can easily see the data and the change of these graphs. So from this, we can see the before grid, and we can see that all the points basically cluster near zero. This basically means that the grid is healthy and is well connected with strong structural integrity. So no change, but once the attacks begin and all of the data is processed, we can see that the points basically spread out dramatically. The red circles basically mean the most persistent features of the time, and the grid has basically broken into isolated islands, which is basically what we'd expect from major infrastructure damages. Not only do we get these, but we also get visual results, and we can see exactly which power stations had failed, which communications lost power, and how the cascade effect can spread far beyond the fire perimeters, as we can see from like the red branches and stuff. So apart from this, there are some challenges to keep in mind as we are processing large amounts of data in real time and also creating a complex network of analysis. And we need to basically think of something fast enough to be useful during actual emergencies, which will be a useful tool in the future. But at the moment, my program is successful in implementing multi-fire analysis as well as expanding on to cover all Western states. Users can basically now analyze compound events, which is when they choose multiple wildfires and that the events run simultaneously. And future plans, looking ahead, we're looking into adding hurricanes, earthquakes, and flooding onto this tool to add on to the specific energy resources and how much, what do you call it? How much damage they can take, essentially. And to leave it off, we also need to think about climate change and how much it will affect the future. And with this tool, it will help communities understand the vulnerabilities before disaster strikes. I believe that knowledge is the first step to building a truly resilient infrastructure for everyone. And I'd like to thank my faculty mentor, Dr. Ofori Boateng, for a new introduction for new programming language and area study, as well as Dr. Tusher for this opportunity and my cohort for overcoming all of these challenges with me. And thank you all for your time.
Thank you. Questions for Brandon? Does your tool consider the fact that electricity can be rerouted? And if, a line goes down, you can
Yes, I
reroute.
believe that there is a tool for that, which also helps the strength of the grid. So let's say like one bus basically goes down, right? The program can identify other possible connections that particular bus has in comparison to other buses. So it kind of
Okay.
just reroutes its position and just sends the electricity that way to access it a new way, essentially.
Right. Okay. And you haven't tested that with like actual emergency services or forest service or something like that, right?
Not at the moment, due to time complexity and stuff.
Yeah.
But right where I am, I think that we are able to move on to like real wildfire instances and like more live data. But yeah.
Yeah, that'd be quite cool. Sweet. Good. All right. We have Prize and Matupom up next.
Let me share my screen.
Can you hear me?
Sounds good.
Can you see my screen?
Yep, looks good.
Okay, give me a moment.
Sure.
Hold on. Okay. Hello, I'm Madhupum.
Hello, I'm Praise Daniels. Can you hear me?
We can hear you, yeah.
Okay. And we're both students of the University of Illinois Urbana-Champaign, and we'll be presenting on Drive, a real-time assistive driving companion, leveraging perception data for non-intrusive conversation audio-based drive alerts. So what is Drive? Drive is a real-time context-aware voice companion for driving. It uses perception models to spot risks, then speaks short, calm warnings, especially about following distance, so drivers can adjust early without being startled. So what is the problem with beeps over the speech warnings that we're suggesting? So basically, beeps can cause distractions by causing a heightened sense of safety that overshadows awareness of dangers. And also, typical voice assistants also don't see the road as well as could you go back? I think you went back too fast. Also, typical voice assistants don't see the road at all. And there's also a gap between the context and communication between compared to using just beeps to warn drivers of the road. So why voice, not just visuals? So as we all know, drivers' eyes are oversaturated with the load of having to look consistently at signs and different things on the road to gain more context. And voice frees this visual load by providing short phrases that reduces the interpretation steps. So our focus is on the unsafe following distance, and we chose this focus over other logic risks that our system could provide because the unsafe following distance is the leading cause of the most common type of car crashes. That is about 29% of them. And Drive watches this by computing something we call the time headway. And this is basically the time it takes for a car to move to get to the same position as the car in front of it. So our car that we drive is called the eco vehicle, and the car in front of it is called the lead vehicle. And time headway is the time it takes to get to that position. So basically, the threshold that drivers feel the most comfortable is about 2 seconds based off of that driving studies. So how we warn, we treat 3 seconds as the minimum safety gap. And basically, if a driver's time headway falls below 3 seconds, our system basically flags a warning. And after the driver's corrected, it will provide a recovery message that tells you that you've corrected your speed. So our architecture, it basically follows from a perception system collects data from front camera in form of frames, and basically it sends the information from the frames. It collects information and performs certain computations with that, and it sends it to a context engine, and the context engine uses that information to generate messages that is sent to the voice module, and the voice module then speaks the output. So basically, our system consists of an object detection model. For this, we use the YOLO V12 medium model, and it basically spots vehicles, pedestrians, and other items on the road, such as traffic signs. And it basically detects about 13 classes. And for this, we had a mean average precision with a 0.5 confidence of 0.46 and a map 5095 of 0.274. This might seem small, but this is relatively good when you consider the PDD 100K dataset that we use as very fast and very complex. And our system also performs road and lane segmentation. And we had a mean intersection over union of 92%, and for the drivable area, and IOU of 34.2% for the lane segmentation. And just like the object detection, 34.2 might seem small, but it's great for this. So we use BikeTrack to track the IDs of cars over different frames, so we can gain more context of the specific lead vehicle. So for the messages we try to keep it under 12 words, and we try to aim for a neutral tone, so we can have early, calm, not just scolding. And we also choose 3 seconds, even though we follow the 2-second rule, so we can have an extra second for the system to effectively communicate the message. And we made a highway tailgating scenario from the Carla simulation, as you can see. And basically, if you could play the video, this scenario we chose just shows how tailgating could occur in reality. And we basically tested that with our system, and we were able to bring this down to about 30 frames per second, and we obtained a stable time headway computation with all that. And we also used the L40S GPU provided by the cluster, and with all that, using that for the inference, we could come under the 30 frames per second, and that is standard for what we want.
When an unsafe tlab is detected, it transitions to monitoring the unsafe condition. If the unsafe operating condition lasts longer than specified duration, it sends a warning event. After sending a warning, it monitors for a return to safe condition. Once a safe, stable condition is confirmed for a set duration, it sends a safe event and resets. Single camera means some uncertainty in distance, whether a cut-in happen. We decide for humility, short suggestions, not guarantee. Driver remain in control. Privacy, respecting, so on device by default. For future works, we calibrate distance better at radar, LiDAR, or whatever possible to expand beyond tlab to merge crossing and vulnerable road user, always with calm, context-aware phrasing and short audio. The takeaway, speaking second at the right moment can prevent tailgating from becoming a crash. Drive give early calm that keep driver in the loop and road a bit safer every mile. Thank you.
Thank you. Questions? You guys were heavy users of the GPU cluster, right?
Yeah.
Yeah, that worked out. Good.
That worked out great for us.
Yeah. And I remember, I think initially you were planning to use cell phones, right? But what is the plan for the integration now? What will you
So
need in the car?
basically, instead of that was we realized that we're not going to be able to perform inference on cell phones, especially using models with that many parameters.
Yeah.
So we just focusing more on just like how we can integrate this into current like ADAS systems, and that is like the advanced driver assistance system they exist, and maybe other like voice assistants such as like the ones in like current vehicles now, like Mercedes B-Max, and just there's some other voice assistants for cars, but they are limited to the in-car context rather than observing what is outside. So we just think about adding this voice module to current ADAS systems already have perception systems that collect all this information about the outside of the vehicle. So we just thought about maybe if we can like integrate that with our system to like understand the outside context.
Yeah. Yeah. Okay, cool. Other questions? All right, next up, Tiffany.
Right, let me just pull up my screen right now. I'll go ahead and share my screen.
Thank you.
Can you see this?
Yep.
Okay, I just want to make sure. And just give me a few seconds, sorry. Good afternoon, everyone. Today we'll be discussing computational modeling in the context of volcanologic deformation. Specifically, we will be exploring an updated model for ground deformation and then explore its numerical stability. We'll then perform a parameter sweep exploring how the physical response of the system changes depending on the defined value of porosity. This will serve as a basis for future work. However, we should take a step back. Why are we interested in ground deformation in the first place? This is Kilauea volcano, located in the southeastern shore of Hawaii. This is just one of over 1,500 active volcanoes that exist worldwide. One of the challenges in modeling volcanic activity is that there are numerous factors that may influence the behavior at any given site, as well as the wide variety of geological differences between locations. As it turns out, it has been well studied that eruptive activity is often preceded by, among many other factors, the swelling of subsurface magmatic chambers. Similarly, the depletion of these chambers generally follows an eruptive event. These actions have a measurable impact on ground deformation patterns. Today, we consider an updated version of a finite element model described in a paper published in 2022, which was authored by my faculty mentor and community partner. It is viscoelastic, modeling both elastic and viscous behavior, and axisymmetric, meaning that there are no changes along the axis of rotation, which reduces the problem to 2 dimensions and thus minimizes the computational burden. The previously proposed model imposed a traction boundary condition on the magma chamber wall that solely involved time-varying pressure. The key difference here is that we now also consider mass variation by adding an additional term to the boundary condition. Due to this change, we must perform convergence testing in order to ensure that the updated model is numerically stable, which involves comparing the numerical solution to the analytical solution. However, because there is not currently an existing analytical solution to our updated model, we instead use a technique called the method of manufactured solutions. Here we may compare the numerical model to an arbitrary analytical solution, as long as it satisfies the governing equations, which typically involves finding a forcing term. The chosen manufactured solution is based on the Moki model, which models a pressurized magma chamber in an elastic medium. We use this to calculate the rates of convergence, specifically the C rate and U rate, which are related to the error for viscous stress and displacement, respectively. Here we see plots obtained from the convergence testing for polynomial orders 2 and 3. The plot on the first slide compares the error calculated using the L2 norm to the mesh size. We see as the mesh is refined, the L2 error decreases. The other plot compares the convergence rates to the level of refinement. According to finite element theory, the C rate should converge to the value of the polynomial order, while the U rate should converge to the value of the polynomial order plus 1. We see this behavior in the plot across all the recorded rates. Given that we have verified the numerical stability of the updated model, we can now use it to model physical phenomena. Consider the effect of gas bubbles embedded within magma that enters the chamber. The parameter phi represents porosity, and we predicted that varying that value would have an impact on the fluid bulk modulus and therefore the components of stress and displacement. So we imposed mass variation at the magma chamber wall using the updated boundary condition and relevant physical information. These plots show some of the output we obtained. We ran 9 simulations, varying phi from 0.1 to 0.9. Here we plot the spatial variation in displacement at the final time step. Greater values of phi are plotted with darker shades of blue. We see that as phi increases, the amplitude of the components of displacement decreases. We see similar behavior when studying the components of stress seen in the next few slides. Again, as we increase the value of phi, we observe that the response across all components decreases in magnitude. This is just one use case for our updated model. We can use this framework in order to simulate various kinds of physical interactions in our future work. For instance, instead of modeling a spherical chamber, we can study ellipsoidal chambers and how the change in chamber geometry affects the displacement and stress components throughout the domain. Additionally, we can calculate something called a transfer function, which defines relationship between an input and output signal selected from points within the computational domain. We would calculate the transfer function as the system parameters change, for instance, computing it for different reservoir temperatures. The current implementation has some limitations. For instance, the updated boundary condition is only applicable to spherical magma chambers, embedded within an infinite elastic medium. A more general boundary condition would be needed for studying other chamber geometries. We also expect the computational burden to increase for higher forcing periods, meaning I might have to make use of a GPU cluster in the future. Finally, the computational time is largely tied to the value of viscosity, suggesting a lower bound might be needed in order to reduce the computational load. Here are some of the tools that I used. We used Python 3 as the main programming language, owing to its simplicity and versatility. Additionally, we used ngsolve, which handles the finite element method computation, matplotlib, which we use to plot the results, and numpy, which handles large multidimensional arrays. Finally, I would like to thank Dr. J. Kopal Hirschman, my faculty mentor, Dr. Leif Karlstrom, our community partner, and Pablo Cortez Castillo, the PhD student that I worked with. Their advice was incredibly valuable and helped guide the direction of my project. I look forward to working with them throughout the next few months. I appreciate your time. Thank you for listening.
Thank you. Questions? how would you validate your model in reality?
I think that with the current state of the model, we've been testing it using I guess theoretical scenarios, and so in actuality you'd pick parameters based on data collected from I guess geological surveys, and then use that in some way to plug that into the model and calculate components such as displacement and stress and compare that to measured values in real life.
Okay. Does your community partner have that kind of data? Or?
I think so, but I think due to the complexity and just like the time that we had, we were just sticking to like more of a theoretical scenario.
Yeah, that's fair enough.
Yeah.
Good. Okay, other
But I
questions?
think in the future, it may be extended to that real life scenario that you were alluding to.
Okay, great. Thank you. Good. Unless there's other questions, we'll move on to Maisha, Karen, and Catherine.
Okay, I'm just gonna share my screen.
Okay. Thank you.
Can you all see?
Yep.
Okay, sorry, 1 second. Good afternoon, everyone. Today we'll be presenting Scram, a project we've been working on that addresses a growing issue people face online, the growing issue of job scams. We're excited to walk you through how it works, why it matters, and the problem it tackles.
Today we'll be going over our team profiles, research and findings, product objective, design development, demo, challenges and solutions, and the conclusion in our future work.
My name is Karen Habib, and I'm currently studying computer and electrical engineering at NYU Tandon.
Hello, my name is Catherine Habib, and I'm studying computer science at Vassar College.
Hello, my name is Maisha Rahman, and I'm studying computer science at Vassar College.
According to Resume Builder, 3 in 10 companies post fake job listings. These listings are often posted, but you're not guaranteed to hear back from them, highlighting how important it is to verify jobs before applying.
The number of individuals using online job markets to find opportunities increased after COVID-19. As a result, online job schemes targeting job seekers have begun to rise as well. The FBI reported that American consumers lost $12.5 billion to cybercrime in 2023.
That's why we built Scram, a Chrome extension that helps you spot fake job listings on Indeed.com before you fall for them, saving you time and frustration in your job search.
With Scram, we hope to empower people who are most at risk. Students actively searching for internships and entry-level jobs, postgraduates entering the workforce, and unemployed individuals looking for legitimate job opportunities.
One of the major tools we used was Hugging Face AutoTrain to train our natural language processing model on a Kaggle dataset with 10,000 fake and 18,000 real job postings. AutoTrain handled most of it, but we also had custom code to fine-tune it to our needs.
Our extension runs on 3 main components: the manifest, background, and context scripts. The manifest files act as a blueprint, defining key details like the extension's name, permissions, and which files Chrome needs to load and run the extension properly. The background script runs continuously behind the scenes, managing the core logic of our extension, including the scam detection processes. Meanwhile, the context script interacts directly with the web page, scanning job listings in real time and flagging any that looks suspicious.
We use Railway, a cloud platform, to host our Python backend, which acts as a language processor, analyzing listing content for scam indicators. Since our Chrome extension runs on JavaScript, Railway allows us to bridge the two using an API calling for easy real-time communication.
Originally, we planned to expand our extension to LinkedIn as well, but since each site had a different console structure, it would require separate code for each. Due to time constraints, we focused on testing and refining our model specifically for Indeed and only Indeed.
On Indeed, users can easily toggle the pop-up to turn on the extension scanning on and off as needed. The pop-up UI is built with HTML and CSS, while JavaScript manages user interactions within the pop-up and communicates directly with the content script to start or stop the scanning process. The content UI plays a crucial role by providing real-time feedback to users about the extension status. It indicates when scanning is in progress and notifies when the scan is complete. If the model finds a fake, the job posting is clearly flagged for the user.
To improve accuracy, we added a feedback feature. A Scram icon appears next to each job listing, allowing users to report any fake jobs the extension missed, or real ones that were flagged by mistake. This helps us continuously improve the model.
Here we have a demo, toggling on and off. And as you can see, scrolling down, it'll start to scan the jobs, and at the end was the feedback. And then this was a separate example of a fake listing.
Developing Scram came with several challenges. Initially, we hosted our Python backend and render, but later migrated to REU for improved performance. Training a model was also time-intensive, requiring extensive trial and error to achieve higher accuracy in detecting fraudulent postings.
For our next steps, we'd like to expand to LinkedIn and Handshake, and also accelerate the speed at which scams can be detected. And to further validate them, we would like to train it with harder scams to detect.
Our immediate next step is to upload the extension on the Chrome Web Store, making it available to real users. This will help us gather valuable feedback and see how well it performs in real-world scenarios, guiding future improvements.
Thank you for your time. Our mission with Scram is clear. We tell scams to Scram. We're excited about the potential to protect users and look forward to hearing your questions. Thank you.
Thank you.
Thank you. Questions? Roberto. You're muted.
Thank you. I'm a little tired, so apologies if you mentioned this and I just completely went over my head. But what is the criteria for deciding whether or not a job listing is fake? I know you guys used a data set of essentially fake job posting to train a model, right? But like to you guys, or rather, what is your understanding of what the criteria is that defines whether or not a job posting is fake?
Yeah, so we looked for keywords such as no experience needed or starting salary of just something outrageous. And we also did research online using Reddit, where they had these postings of known scams, and they also linked them for us to test it on. So we could see if it worked on those scams as well.
So you're looking for like keywords and then also just matching it up to existing known scams, right?
Yes,
Interesting.
correct.
Cool. Great. How did you deal with data privacy? Is everything stored locally, or where's the data sitting?
We didn't really have any issues with LinkedIn. We got rid of the errors that we had before, where they wanted us off the page after we stopped using Terminal,
Okay.
and we started using our new backend.
When you were scraping their
Yeah.
website. Yeah. Okay, understandable. Yeah. Good. Cool. Well, it would be nice to work with Indeed directly, right? See what they think then.
Yeah, hopefully we can get sponsored.
Yeah. Awesome. Thank you. All right. Unless there's other questions, we have Silas as our last speaker in this session.
Okay, can you guys hear me?
And we can hear you, yeah.
Okay, perfect. Okay, you should be able to see my screen now.
It's coming up. All right.
Okay. Are you able to see it?
Yep.
Sorry, give me 1 second. Okay. Good afternoon, everybody. My name is Silas McNeil, and I was a part of the tlab High School Summer Internship. And today I'll be discussing what I worked on over the summer. My project is titled Using Neural Networks to Predict Diabetes and Glucose Level Jobs. So the motivation behind this project started when my older brother was diagnosed with diabetes, and ever since he was diagnosed, he'd had issues with his CGM and the treatment that was being used. So I wanted to create a better system. So first, diabetes is a disease where your pancreas doesn't produce enough insulin or where your body can't effectively use the insulin that it has. So this results in a surplus of glucose within your blood. The goal of this project was to explore what networks gave the best results in the predicting glucose level drops and diagnosing diabetes. Specifically, the networks are predicting if a glucose drop is due within 30 minutes given an hour of readings, and if a patient has diabetes given 8 inputs. So CGMs are reactive devices. So this project explores the potential for using neural networks as a predictive device. So rather than waiting for something to change, we want to predict to find the change before it even has time to happen. So the Taipei Medical University created a similar project where they tested blood glucose levels using an LSTM, WaveNet, and GRU to predict glucose levels. My project used an LSTM, spiking network, and reservoirs to predict the glucose drop. So a recurrent neural network is a class of artificial neural networks that use input at the current time step along with the hidden state to retain contextual information. So these are usually used for processing sequential data like language or text. So an LSTM, or a long short-term memory network, is a type of recurrent neural network that's great at remembering important information over long sequences. So it uses a series of gates to remember what to forget, what to keep, and what to leave out. So for my results, I got 24 true positives, 168 true negatives, 14 false positives, and 2 false negatives. It had a 92.3% overall accuracy with a 63.2% precision. Now, a spiking network is a network where the neurons communicate through signals called spikes. A neuron only fires a spike once its membrane potential builds up to a specific threshold. Once that spike is fired, the signal is propagated to the connected neurons and their potentials are now adjusted. For results for the spiking network, I got 22 true positives, 147 true negatives, but had 35 false positives and 4 false negatives. Overall, we had an 81.3% accuracy with a 38.6% precision. Now for the diabetes test, I got 16 true positives, 46 true negatives, 7 false positives, and 9 false negatives. Overall accuracy of 82.5% and a 69.6% precision. Now, reservoir is a network of randomly connected neurons that creates a short-term memory of what has been seen. So the reservoir itself isn't trained, only the readout layer knows how to read the signal that's passed from the reservoir to the readout layer to produce the final output. The reservoir got 15 true positives, 163 true negatives, 19 false positives, and 11 false negatives. Overall, it had an 85.6% accuracy with a 41.1% precision. For diabetes, it got 8 true positives, 44 true negatives, 9 false positives, and 18 false negatives. This gave it a 44% accuracy, and when predicting diabetes, it was incorrect more times than it was correct. Now, a multitasking network receives at least 2 inputs of related data, and it gets passed into a central layer to learn general features from the input, and then task-specific layers make predictions on the input. An example would be discriminating photos of flowers based on color and type. So I tried using a multitasking network, but no viable results were produced because the data sets were viably different. The diabetes data set is static and not changing. The glucose was time-based and it was given as readings. So overall, the LSTM had the best results for the glucose. The reservoir had second best in glucose, but worst in diabetes prediction. Spiking had the worst result in glucose, but the best in diabetes prediction. So in conclusion, the recurrent neural network ranked first, the reservoir in second, and the spiking network last. For diabetes, the spiking ranked first and the reservoir ranked second. A multitasking network was attempted, but not successful. Some potential future work is further optimizing and improving my network models, implementing the network on a Raspberry Pi using a neuromorphic chip, and further prediction horizons with smaller time windows. So rather than having 1 hour of readings fed into the network to predict 30 minutes ahead, maybe 15-minute windows to predict an hour ahead. I'd like to extend my thanks to Dr. Tusher for this opportunity, and I'd like to thank all the interns I had the opportunity to work with over the summer.
Thank you. Questions for Silas? I was wondering how you made sure that the spiking neural network was actually converged.
Yeah, so when I ran it at around 1,000 epochs was when it would begin to converge, but at that point it was taking about 5 to 10 minutes to compute, and so I figured it'd be a little bit unfair for the testing purposes because all the other networks were tested from 1 to 300 epochs, and they all converged within that range.
Right, but it's quite common that spiking neural networks will take longer for convergence. So I think you want to make sure that all of the networks converge no matter how long it takes. And was that the case?
Yeah, so all of them did converge. Spiking did converge. Like I think it was at 1,000. I think it was 1,300 epochs was when it finally converged.
I see. And did you also vary the number of neurons in the networks?
Yeah. So for the spiking one, we had 128 neurons. Reservoir, we had 128. And then I think for the LSTM, we had, I think, just under 200.
Okay, but are you confident that this was enough for the spiking neural network?
When I tested more, I actually saw worse results, so I had to back the amount of neurons. So from what I saw, I thought it was
Okay, that sounds good. Yeah, great. Thank you. Other questions for Silas? All right, folks, we have 6 minutes, a 6-minute break. Then we have our 4th session with another 6 talks. Hopefully you can hang out and be there for those 2. So we'll see each other in now 5 minutes. 5-minute break. Okie dokie, welcome back. For the last session, we have Tisaga and Rivi as our first speakers. Whenever you're ready.
Hi, everyone. I'm Tisaga, and I'm here with Rivi, and we're going to talk about StriveBot, our WhatsApp-based virtual guidance counselor. So our main goal was to close the gap in college guidance counseling that we have in Sri Lanka, because the most schools are in rural areas and they don't have access to counselors or other kind of resources to guide them through their higher education and career journey. So the main reason for that is we have a very scattered network that doesn't have good coverage anywhere in the country, or like for the most places in the country. So using web-based tools or other kind of medium is hard, and it's difficult for everyone to access. So that's why we're using WhatsApp as the interface to provide the chatbot and advice. So our mission is that we choose high-achieving, under-resourced students from all around the country, and we match them with professionals who has experience in their particular career paths, and we help them achieve their dream job or research or career, and we help them get there. So that's why we're building StriveBot. It's a WhatsApp-based chatbot that based on our custom knowledge base and also has access to the internet to find answers and help them guide their college application process, research application processes, and like everything like that. Anything related to career and higher education, our bot can handle those conversations. The reason for using WhatsApp, as I mentioned before, is because it's low bandwidth and it's very easy to scale. And because it's text-based, we can easily monitor the progress. And if there's any issues with that, we can always kind of get back to the base of it and like make necessary adjustments. We primarily use Gemini API as our large language model, and it has the ability to pull knowledge from the web. And also we have a custom vector database that we built on Qdren that collects all the knowledge and builds a vector database to use when a user asks a question. So we use a service called Bright Data. We got an offer to use their service to scrape data out of websites, publicly available websites, and we use that in our bot. And all of our answers are based on a source. So with every answer, the user will see the source, where it's coming from, and we make sure that it can have up-to-date information at all times. And if it's unsure about something, it won't give an answer and say we don't have the information at the moment, and would guide the user to a particular resource that it think would be helpful. So we have a very scope-limited, privacy-preserving counselor persona that we've very carefully crafted over a couple of months, and we've tested with a lot of its cases, and we have found it to be very effective in kind of protecting and doing only what it's supposed to do, and not exposing private data or letting abuse the system and our token counts as the chatbots goes public. So first of all, we created a proof of concept using LangChain and Face. It helped us build the database and only pick the relevant information when uploading tokens to the AI. Because if first we had a lot of tokens, that our token count was so high, we had a very big expense. So we kind of found this method to be very helpful in cutting down costs by like 90–95% as we implemented this. And I'm going to hand over to Ravi to continue from here.
Hi, I trust everyone can hear me. So yeah, in order to make our work a lot easier, we used free hosting on a GUI based workflow, and we decoupled development from deployment and moved to a more stable setup, as Cesar was saying. We wanted to be able to for the chatbot to be able to converse not only in English but in our native languages, Sinhala and Tamil. We have validated bilingual support so far, English and Sinhala. And we basically the files first land on the Google Drive, and then the agent embeds and stores in Qdren, as Jessica mentioned. So that's how retrieval works for the conversations. In terms of testing, we have so far run a 1-week pilot with 5 users, volunteers from our organization, with 10 questions each. Mentors evaluated accuracy and usefulness. So these mentors rated 80% of answers accurate and helpful, 10% partially correct, and 10% incorrect. We have been iterating based on the feedback that we have gotten. Top topics include admissions, scholarships available, financial aid, testing. We have particularly taken use of, are hoping to make use of the Bright Data web crawlers for more specific data. Key risks include hallucinations and privacy. We mitigated that with curated context, safety prompts, and we plan human follow-ups. Average response was 7 seconds. And next up, we are hoping to include a production-grade RAG, opt-in memory, human escalation, and rigorous evaluation to scale responsibly. We hope to do more of an alpha test in the future. And we're seeking partners for a larger pilot, domain data to ground answers, and backend API expertise to harden deployment. We just want to, the summary, gonna skip through that. And we're just gonna acknowledge Professor Christoph Teuscher for this opportunity, and everyone who was part of this program. We also want to acknowledge the effort put in by the organization's team. And yeah, thank you.
Thank you. Okay, we have time for a quick question. How do you make sure that the information is up to date?
So like as I said before, the bot has the ability to search the web, and if it finds something that's up to date, more up to date than the ones in our database, it automatically prioritizes the data that they found on the web rather than the stuff, the information on the database.
On the
We
I
are,
see. I see.
yes,
So
we're trying to build like a human interaction model where it'll let us know that there's outdated information, but
Okay.
we're still working on that.
Okay, so you're periodically scraping the web page.
Yes, we have a Bright Data crawler, web crawler that helps us with getting all the information in a like a
cool
interval. Yes.
All right, thank you. Other questions? Okay, moving on to Marcus. Thank you. You're muted.
There we go. Is it sharing just fine?
Yeah, sharing looks good. You're all set.
Well, hey everyone, my name is Marcus Campbell. I spent the summer in the Tusha lab with the focus of bringing benchmarks from simulation to real-world application. In the lab, we built a physical version of a widely used benchmark simulation for reinforcement learning called the cartpole model. What are benchmarks? So benchmarks are tests and set standards for comparison, and in AI, they allow us to kind of test algorithms and accelerators on the same challenges like the cartpole, so that results can be compared fairly across labs and models. Why we use benchmarks? Well, they give us researchers a common way to measure progress. Without them, it's hard to know if new algorithms or hardware are truly better or just tested under easier conditions. The current reinforcement learning tools that are out there are some of the simulated tools by OpenAI's Gym. You have the cartpole model itself, the lunar landing, car acceleration, as well as a navigation search for the Santa Fe trial. Why simulations for benchmarking? Honestly, simulations are a little safer. They are more cost effective and they're widely accessible. So they allow us to kind of create an environment that it would be a little more difficult. But with that, you have some shortfalls. Due to that, we have some potential sensor noise that we're not capturing, some failures that we're not capturing, and some complexities of the real world environment that we simply just don't capture. So here's a little example of the actual cart that we built running. This is a basic feed-forward neural model that it was running on it. And this is just going through some of our different testing just to make sure it works. So what actually is going on? So we have the cart pole, which is a 4-vector input, cart position, cart velocity, arm angle, and arm angular velocity, all given to give a right-left output to keep the cart pole balanced. In our system, we used an array of different electronics. In our system, we had an encoder that passed data to a Raspberry Pi, to an Arduino, to a stepper driver, and then that moved the actual motor. And this is why we would use this for why bring the physical one in? So the physical one brings in a lot more realistic challenges like sensor noise and the environment, given that the rails are moving. And some of the things that we actually realized were like mechanical wear. Our timing belt actually began to loosen over time due to some different circumstances with heat and some of the materials that we were using. But when we finally got it built, we have this 4 levels of tasks that we're doing here, and we have some KPIs built in and easy and hard levels per the task. For task 1, it's a simple swing up. It's going from your 0 degrees hanging down, and the idea is to swing the arm up to 180 degrees with a 5-degree standard deviation off of that for its success. For task 2, we balance the pole, so it would already be starting at the 180-degree position. And then the goal is to keep it within plus or minus 15 degrees from that 180-degree position. In task 3, we swing and balance, so it combines task 1 and task 2. So you have to start at 0 degrees, get up to 180 degrees, and then maintain that over time. And then in task 4, we have the fall recovery. So once we're going to start at the 180-degree position, we're going to let the arm fall after it passes the positive or negative 90-degree threshold. The model will actively try to move the cart back up, or the pole back to the top. Easy versus hard levels, we have the 4-vector input that goes down to the 2-vector input. So out of this, you lose your angular velocity of the arm and also the velocity of the cart. We are working on remote device connection right now. I had it going through Tailscale VPN with fast APIs so that we could connect external devices to this machine so it can make the right-left choices from the external device. And that leads us to where we plan to open source this tool for any other researchers, any algorithm builders. We want to make sure that you guys have the opportunity to test something on a real world example and see how well your model or hardware performs. And yeah, I just wanted to say thank you to everybody in the lab, Crow, Tucker, Dr. Tusher. It's been super fun building this system. Learned a lot doing it. And then also here's a QR code if you want to scan that to jump on the quick list of anybody that would like to potentially use this for their own models or devices.
Thank you. Questions for Marcus? What was the most recent setback?
The most recent setback was in material science. So I don't know if you can see my cursor.
Yeah,
But the motor was living in this casing right here, which was made out of PLA, which is a material that we used for the 3D printed box built with FreeCAD. And the motor over, I think it was on its episode 20 of its learning algorithm, decided to get really warm, and it went ahead and melted that plastic there. So we've had to refactor that complete area with some different reinforcements that are non-meltable. And then we've also had to add in some cooling systems as well. So we're finishing up that cooling system work right now. Hopefully have this online within this next week.
Great. Good. Other questions for Marcus? Good. So yeah, scan the QR code, or you can post a link in the chat too, and folks can sign up whenever you.
Yeah, I'll grab that link
have an
right now.
API, we'll make it public.
Awesome.
Good. Thank you. All right. Is anybody from the group of Sara Chawla, Angelina, Ritzika, or Ishani here? I do not see any of those folks. Seth, are you waiting for Heejun?
Yeah, I switched my presentation time. I haven't been in contact with him today, but I switched it to accommodate for him, so I think he was planning on coming. But
Okay,
if you need me to go, I can. But yeah.
No, let's wait 5 minutes then. Okay, we get an extra break, folks. Let's start at 1:21 in 5 minutes. Since the next group is not present, it seems. Okay, sounds good. 5 minutes. All right, thank you. All right, welcome back again. Seth, I don't see Heejun, but I think you can start setting up and get going. We'll have the recording if.
Okay, I'll start sharing my screen. Can you see my screen?
Not yet, no.
No?
No.
Oh wait, I did not hit share screen.
Okay.
Yeah, I was like, oh my gosh. Okay, there we go.
All right, now we can see it. Yeah.
Okay. No.
Can you make it larger or yeah?
Yes.
Yeah.
Hold on. Okay, can you see my screen now?
Yep, looks good.
All right.
Go ahead.
And
Yeah.
I'll turn on the autoplay. All right. Hello, everyone. My name is Savannah Milburn, and I am part of the National Science Foundation REU program at Portland State. And I'm going to be talking about what controls air stream temperature dynamics in the Clackamas River Basin in Oregon. And before we get into controlling factors, we need to ask, what does our current environment look like? Climate change and urbanization has caused air temperatures to rise, which then cause warming in streams and rivers all around the world. Warming temperatures harm water quality and change how water moves throughout an ecosystem. Specifically, altered rainfall patterns, increased sediment runoff, and reduced cold water inputs can shift water temperatures. Specifically for the Clackamas River Basin, Oregon streams are home to cold water fish like salmon that have uniquely adapted thermal regimes. Changes in stream temperature greatly impact fish migration and spawning, leading to increased fish mortality rates. River streams also provide drinking water, recreational activities like hiking, whitewater, and kayaking. And without a healthy river system and with increased extreme weather, drinking water quality and quantity are damaged and riverine organisms are harmed. And here's where my research comes in. Thermal sensitivity is the relationship between air and stream temperature. This dynamic value describes how much stream temperatures change with a 1 degree increase in air temperature. Usually, researchers predict stream temperature instead of thermal sensitivity using predictors like air temperature, stream flow, and elevation. However, with my research, by explicitly predicting how sensitive streams are to changes in air temperature, we can directly identify vulnerable locations in the Clackamas River and protect the drinking water and fish. Now, how do we identify drivers of thermal sensitivity? In my research, I use 3 models, multiple linear regression, random forest, and spatial stream network model to find the most significant drivers of thermal sensitivity. First, daily mean stream temperature was regressed on daily mean air temperature for 72 sites in the Clackamas River Basin. This linear regression revealed each site's specific thermal sensitivity value, which was then related to 40 variables describing unique site characteristics. Correlation analysis and this linear regression between thermal sensitivity and the 40 covariates revealed 5 significant predictors, which explained about 63% of variability in thermal sensitivity. Streams underlain with high cascade geology and with higher base flow were substantially less sensitive to air temperature, which could be because they're located at higher elevations that carry more cold groundwater due to the more porous cascades geology. In contrast, streams with more upstream developed and agricultural land were more sensitive to changes in air temperature, which suggests increased human development weakened stream thermal regimes, likely by removing essential vegetation. Next, a random forest model was used to identify significant thermal sensitivity drivers without assuming linearity. This model used 400 tree-like structures called decision trees to predict out of the same 40 predictors to find thermal sensitivity relationships. And the final significant predictors are determined by a majority vote among these 400 individual trees. Random forest identified base flow and high cascade geology, as well as elevation as significant predictors. But the last model that I used was a spatial stream network model, which accounted for inherent stream spatial influences. Streams have a network structure and are influenced by flow direction and flow distance. And using the same 5 drivers from the linear regression model, this spatial stream network model revealed significant spatial influences as flow-connected spatial influences explained about 57% more variability in stream sensitivity. When comparing the 3 different models, the spatial stream network was the best fit for the stream temperature data, and it also accounted for the most variability, as shown by the cross-validation R-squared in the previous slide. When looking at all of the significant predictors from each model, we can see that geology related to the Cascades mountain range significantly influenced thermal sensitivity, as well as the amount of vegetation, which can impact shading and runoff. And although these variables were significant predictors of thermal sensitivity, the linear and random forest models don't account for these inherent spatial influences like the spatial stream network model did. And analyzing why streams are more or less sensitive to warming temperatures can inform management and conservation efforts for water suppliers, ecologists, and landowners, better protecting water quality, water quantity, and cold water fish. And I'd like to thank Dr. Tusher and Dr. Chang, as well as Michael, who's a PhD student under Dr. Chang, and all the students who helped me learn this summer. Thank you.
Thank you. Question?
Did you look at anything like salmon populations over the past couple of years or decades compared to the thermal sensitivity changes?
I did not look at that specifically like within the research, but there's literature that exists with that, I think. Yeah.
Yeah, they do salmon ladder counts every year, so they have really good data for it.
I was wondering about a similar question because there's all these dams, and I think the Clackamas River is an example where they removed the dams. Is that something you consider or you could consider? The fact that there is a dam, that dams potentially get removed?
I'm sure there would be, I didn't look at that specifically in my research, but I think there would be a way if you accounted for like the location of the dam, of course, in the network and how that like nearby sites maybe were influenced from that.
Right.
Is
Yeah.
how I would think to go about that, and maybe like factoring that into the regressions and predictions.
Yeah, that could be interesting. Yeah. Good. Other questions? Okay, thank you. If not, we have Palayapna and Vivek and Aman. I see some of you guys
Yeah.
online. All right, who's gonna share the screen?
Yeah, I think Vivek's sharing his screen.
Oh, okay, Vivek. Okay, we can see it.
All right, let's begin. Hello, everyone. We are in Team Examic. I'm Aman. My teammates are Palniappan and Vivek. And skin diseases affect over 85 million Americans every year, costing billions in healthcare. And globally, they're one of the top causes of disability. But the real crisis isn't just the disease, but it's access to accurate diagnosis. As you can see, over 223 million people worldwide are affected by skin diseases in total. But within the US, it's just 85 million. All right. Specialists are scarce in many regions. Dermatologists, although, can reach 97% accuracy, but most patients see general practitioners first, whose accuracy is far lower due to limited training in skin diseases. And without accurate early diagnosis, treatment is delayed, which can cause conditions to worsen and healthcare costs to rise. The problem isn't just medical, it's also economic and social. Moving on, deep learning, especially convolutional neural networks, can match expert level performance in visual recognition, and the challenge is getting that power directly into people's hands anywhere in the world. All right.
Okay, so CNNs today can match expert level visual recognition. They usually break images into layers and they detect edges and patterns and then eventually create a final evaluation. And in our app, we plan to use CNNs because they provide more agency from the user. We can get dermatology from anywhere in the world, and they're really light and easy to use, and we can put them in this mobile app. So this is our final goal.
Yeah, and the training pipeline that we used is shown below. So first we collected the data and then pre-processed it based on our model, which also includes converting it to a TensorFlow data set. And then we had to initialize our model architecture that we chose so that we could eventually train the model and then evaluate the model to see what needs more fine-tuning. So the data set that we used was a publicly available Kaggle data set. It has around 27,000 images spread across 10 different disease classes. And we chose this data set because it has medical grade images that helps us train our model better and helps it identify these skin diseases in, like, for example, when you have not ideal lighting conditions. And the data pre-processing that we did was normalizing these disease classes because some of them had around 8,000 and the other classes had around 2,000. So we decided to randomly sample around 2,500 images for each class. And we then resized it into 224 by 224 and then converted RGB into BGR and then zero-centered it based on our ResNet model weights. And we also finally converted it into a TensorFlow data set. And we used a TensorFlow data set because it's a much better efficient method to load in pictures as it's based on batches, which is far superior than loading all of the 27,000 images into memory. And as you can see, this is our the shape of the data set, which is 32 by 24 by 224 by 224 by 3, where the 32 represents the batch size and the 224 by 224 is the actual dimensions of the image, and the 3 channels represent BGR. And it's also easy to train with later.
We also use synthetic data to improve our model and improve our data sets. And why do we use GANs and how do we use them? Even with 27,000 images, some diseases were underrepresented, and we used GANs to make the data set richer and more balanced. So basically, we trained a pix-to-pix style GAN to take a binary mask of a lesion and generate a realistic skin image. These synthetic outputs were added to our dataset, giving the CNN more variety to learn from. Here you see the input binary mask, which is the input basically, and the one on the bottom is the target image, which is the RGB image of the binary mask. And from that, the GAN generates a synthetic output. And since they're extremely visually close to the target, this helps the CNN learn patterns it would otherwise miss, such as lesion shapes or change in gradients or color. And this is before we applied the cap to our 7,000 images, this was the training results from the entire unedited data set. Basically, back when we had 30,000 images back in the data set, we saw that the initial validation accuracy reached up to 85.1%, but with GANs, we were able to bring it up to 85.8 to 85.6. So there was a slight increase in validation accuracy.
Yeah, and another important topic that we used in training our model was transfer learning, where transfer learning refers to using a pre-trained model with the existing weights to help in a new task, which in our case is skin disease detection. And we use transfer learning as a feature extraction tool where we use the ResNet 152 model with its pre-trained ImageNet weights, which the ResNet 152 model accurately can detect edges and lines. And we use that to detect the edges and lines of these diseases and then pass these on into our dense layers that help us accurately identify these diseases. And this is our model architecture, where the ResNet 152 is our initial layer that acts as the feature extraction layer. And then we have 3 dense layers and a dropout layer to help with the overfitting. And the training methods that we used were, first of all, fine-tuning hyperparameters, such as the number of layers we kept frozen and unfrozen in the ResNet model. And we also used early stopping to prevent overfitting, which in our case, we found out that it was epoch 9 where the model started to overfit more. And we also used a learning rate scheduler so that we can gradually decrease the learning rate as it starts to overfit, which, as you can see in Epoch 7, it started to overfit, and the scheduler reduced the learning rate that helped jump the validation accuracy.
So these are the graphs of our model, and on the left you can see the loss curve as the model trains over epochs. On the right you can see its training and validation accuracy going up, and then eventually curving off. And then in the middle you can see the diffusion matrix generated, and we got a final testing accuracy of 89.34% for the model. So this is our application where we plan to integrate the model in, and we built it in React Native. So you can scan your skin, capture an image, and it gives you a diagnosis, and it tells you how likely that you have eczema and the confidence level of the model, so that so there's no false diagnosis if you and the impact that our model might have. So clinics across the US could use this model to help with their regular use, increase their accuracy. It could speed up their diagnosis. It could cut patient wait times, because we have a shortage of doctors in the US. And we could, as this map shows, there's plenty of underserved areas in the US where care, where there's definitely use for that care. And this model, we believe, could be helpful towards that. But however, in the future, we could definitely improve the accuracy of the model even more. We could increase the diversity of the data set. We could train on a larger data set. We could potentially look more into GANs. And we could also explore different structures, like the mixture of expert structure that that OpenAI used for their recent OSS model.
Thank you. Questions? So I think somewhere you mentioned that the accuracy of a human is actually similar. Is that really true? Like around 80 or 90, just below 90%?
Yeah. For experienced practitioners, their accuracy is pretty high, but the issue is that these experienced practitioners are quite rare to find, and they're usually in most developed countries. But when you go to a general practitioner, it can vary, as they're not trained on skin diseases.
Oh, it will be much lower for a general practitioner.
Mm-hmm.
Is that what you're saying?
Yeah.
I see. Okay, good. Cool. Other questions? All right, thank you. We have, last but not least, Araf and Valentine, I guess. Araf, are you the only one presenting?
Yeah, Valentine's on a plane right now.
He's on a plane. Okay, good.
Yeah.
All right,
Thank you for accommodating us, though.
Oh, of course, yeah.
Um,
All right, whenever you're ready.
Yeah, so me and his project was creating an kind of a mobile app to help you set goals for achieving a goal, and it helps you create SMART goals. So pretty much you can enter in whatever you want, and then based on the SMART kind of goal framework, it creates a goal for you and creates like checkpoints for you that helps you keep going. Really, the reason for this is because a lot of the like goal setting apps we saw or like used currently are really just kind of reminder apps more than anything, but found like for long-term goals, really, while you're doing it, your goals tend to change. And so over like 1 or 2 years, if you have a long-term goal, it really is helpful to have like a chatbot. So that way, when you want to make a change to your goal, you can just enter that in and it helps you, recreate those checkpoints, recreate what you need to do next. So it's really useful for creating like smaller steps that are a lot more achievable. And so one of kind of our earliest issues was having a chatbot that would not cost a lot of money and that could also be used on like a website or an app. And so we ended up going with Base 44, which is kind of like a create your own app with AI, but it's kind of not so great. But we were able to use it, kind of the base of it for the chatbot, and then able to kind of insert our own code to really customize the layout and train the LLM to what we wanted it to do. So this is what it kind of looks like right now. So you kind of have like an AI assistant, which, is customized to you and you can talk with it and it helps you kind of set those goals as well as like progress trackers. One of the biggest things that we want to add was a like profile page. That way, when you first log into the app, the first thing, the app already knows a little bit about you. So that way it knows like your gender, your age, your occupation, and then some of your, smaller short-term goals. That way it really helps you. It can really customize what it says just for you specifically, and based on where you are right now in your stage of life. And so we haven't been able to get it like large scale tested as much as we wanted throughout this project. Me and him both plan to like continue with this project, but we were able to get a like small group of family and friends to test it who, had good things to say about it. Of course, that is kind of like a biased group of family and friends, but I think the biggest thing was giving us feedback on the website itself. So like tweaking the user interface, and then there were times where our output was a little bit not as good as we wanted it to be, or maybe a little bit passive aggressive, which is not good. So we were able to fix that, as well as like even in this small group, like there was an issue where someone didn't have JavaScript enabled, which kind of broke our website. And like not having JavaScript enabled is like most 99% of people probably have it enabled, but it really just kind of showed us that you really have to account for the 1% when you're building something like this. And so it really made us go back through every step of our process and make sure that we were able to create the best product for everyone out there, even people, for scenarios we might not expect on the daily basis. So kind of the stuff we're working on right now is we have it kind of in a app stage for like a website. We're trying to get it. I mean, we have an APK package ready to go and ready to upload to the Google Play Store. However, the Google Play Store has a lot of challenges in like uploading something like this. You have to go through a whole bunch of rigorous testing from their front, as well as like we have a privacy policy, which we will have to make a whole bunch of tweaks to get it, with their legal standards. You have to get a rating for like a content rating. So that's another like phase of testing you have to go through. And these testings usually take, weeks to months. And so we have it all ready to go. We're just waiting on those test results, as well as like creating an app and like portals in our app, so that specifically for those testers to use instead of the general audience. And so after it's good to go, once it's uploaded to the Play Store, we hope to get it, wider testing. So putting it out on like forums and threads online, and getting, random people to test it in their everyday lives. And so our next steps are kind of, uploading that to Google Play. Like I said, it takes a long time and a lot of testing, as well as a little bit of money. So we're trying to get that all good to go. And then, like I said as well, continuing testing with a wider audience. Yeah, thank you.
Thank you. Questions for RF? Are you aware of any other app who does in a similar way what you're trying to do?
I mean, there are a plethora of goal setting apps. One of the most common ones is like Coach. There's a few coaching apps. But like I said, a lot of them are more checklist based, where you create, like, you enter your own goals and then you create your own checklists.
Okay.
The idea behind this app was it helps you create that checklist for you.
And how does it work over time? Over time, like you said, whatever long term, like could be a 2 years goal. What is the chatbot helping you with on the way? That part I didn't quite understand.
Okay, yeah. So, like, personally, I have a goal right now to, like, I'm trying to learn a little bit more about finance and investing. And so, like, short term, I could ask it, like, okay, tell me a little bit more about that. Help me set a goal. And it would be like, okay, why not, start small, start with a few bucks in like a small fund. And then over time, as I start to get more experienced, I can be like, okay, I want to, go further. I want to explore more about finance. And so I can tweak that goal to maybe it creating a new set of kind of advice or checkpoints where it kind of leads you towards maybe a little bit more advanced sections of finance, or and you can apply that to like health. If you have a goal to become more healthy, you might not know where to start, and so it starts you small, and then you say, okay, now I want to be a little bit more proactive, and so it helps you tweak those goals to be a little bit more specific over time.
And then after a month, it has you sign up for a marathon or something.
I mean, if you want to, yeah, it definitely might suggest that.
Okay, cool, good. Other questions? All right, if not, thank you all for making it to the end. This concludes our symposium. Great job, everybody. This was very good in so many ways. It's always really cool to see the end of these projects. And I should say there isn't usually an end, but the end in terms of presentations. Right, great job, everybody. And we'll be in touch. I'll share the recording, and we'll also be in touch regarding proceedings and other follow-up items we may have. So thank you, and talk to you soon. Bye.